Humans have forever pondered about our existence in the universe. Questions have been solved, but there is still yet so much we don't know. From the mysteries of our solar system to the mind-bending physics of distant galaxies, we'll journey through a universe filled with unexplained mysteries. Join us as we delve in the most fascinating space facts about the universe. The Sun is an astonishingly massive star at the center of our solar system, and its sheer size is difficult to comprehend. To give you an idea, around 1,300,000 Earths could comfortably fit inside the Sun. This staggering number illustrates the incredible scale of our nearest star. The diameter of the Sun is approximately 1,400,000 kilometers, which is about 109 times the diameter of Earth. When you think about the volume, which is a much more significant factor in determining how many Earths could inhabit that space, the difference becomes even more pronounced. The Sun's volume is roughly 1,300,000 times that of our planet. These figures highlight not only the grandeur of the Sun, but also its critical role in supporting life on Earth through its warmth and light. Without the Sun's energy, our planet would be an inhospitable frozen world. Understanding the size comparison between Earth and the Sun helps put into perspective the vastness of our solar system and the intricate dance of celestial bodies that govern our existence. Considering the immense scale of the solar system can be awe-inspiring. The Sun serves as the backbone for the orbits of the planets, and this magnetic pull is essential for maintaining the delicate balance that enables life on Earth. Attempting to stand on Jupiter would be an impossible feat due to the planet's unique characteristics. Unlike Earth, Jupiter is a gas giant, composed primarily of hydrogen and helium, which means it lacks a solid surface. If you were to descend into Jupiter's thick atmosphere, you would likely find yourself engulfed in swirling clouds of gas and extreme pressure long before getting anywhere near a solid ground. As you ventured deeper into Jupiter's atmosphere, the conditions would become increasingly hostile. The pressure would rise dramatically, and temperatures could exceed several hundred degrees Celsius. This unrelenting environment would crush any human and obliterate any spacecraft long before anyone could hope to achieve any sort of landing. The intense gravitational force experienced on Jupiter is another factor to reckon with. It is more than 2 times that of Earth's gravity, which would make movement incredibly difficult, if not impossible. Furthermore, Jupiter is home to ferocious storms, including the famous Great Red Spot, which is a massive storm raging for centuries, much larger than Earth itself. The winds in these storms can reach astonishing speeds, making the atmosphere turbulent and chaotic. Even if one could somehow survive the crushing pressure and extreme temperatures, the violent weather would pose a severe threat. Standing on Jupiter is beyond the realm of possibility, given its gaseous composition, extreme atmospheric conditions, and powerful gravity. It serves as a reminder of the diverse and often inhospitable environments that exist within our solar system. Saturn's rings are strikingly prominent and easily the most stunning feature of any planet in our solar system. Their exquisite visibility results from a combination of factors that make Saturn unique among the gas giants. Unlike Jupiter, Neptune, and Uranus, which all have rings, Saturn's are vastly larger, more complex, and constructed from a variety of materials. The rings are composed mainly of ice particles, along with smaller amounts of rock and dust. This icy composition makes them extraordinarily reflective, allowing them to capture sunlight and create a dazzling spectacle. The size of these ice particles varies significantly, ranging from tiny grains to massive chunks several meters across. This diverse range contributes to the rings' intricate textures and brightness, making them prominently visible even from Earth with small telescopes. The formation of Saturn's rings is believed to be a result of several processes, including the remnants of moons that were torn apart by the planet's strong gravitational forces, or the material that never coalesced into a moon in the first place. This means that Saturn's rings could be relatively young in the cosmic timescale, potentially forming in the last few 100 million years. Their evolution continues to be shaped by gravitational interactions with Saturn's many moons, which can either push materials outwards or allow them to spiral inward. While other gas giants possess rings, they are much fainter and more difficult to observe. The interaction of Saturn's rings with its environment, including its numerous moons and the planet's magnetic field, enhances the complexity and beauty of this iconic feature. Each of these elements contributes to the reason why Saturn stands out, offering us a breathtaking view of rings that tell a fascinating story of cosmic interactions and dynamics. A day on Venus, which is defined as one complete rotation on its axis, lasts about 243 Earth days. This prolonged rotation is notably longer than a year on Venus, which takes approximately 225 Earth days to complete one full orbit around the Sun. This means that a day on Venus is longer than a year, creating an intriguing and perplexing aspect of our neighboring planet. The unusual length of a day on Venus can be attributed to its slow and retrograde rotation. Venus spins on its axis in the opposite direction to most planets in the solar system, including Earth. While Earth rotates on its axis from west to east, Venus rotates from east to west. This retrograde motion means that on Venus, the Sun rises in the west and sets in the east, which is contrary to our experience on Earth. Additionally, the tilt of Venus's rotational axis is a mere 3 degrees, meaning the planet does not experience significant seasonal variations like Earth does. The combination of this minimal tilt and the slow rotation results in long periods of daylight and darkness. Despite the long day, Venus has an incredibly thick atmosphere composed mostly of carbon dioxide, which creates a powerful greenhouse effect. This leads to astonishingly high surface temperatures, far exceeding what we experience on Earth, making Venus the hottest planet in our solar system. The slow retrograde rotation of Venus contributes to its lengthy days, coupled with minimal axial tilt, resulting in a unique atmospheric composition that shapes its climate. These characteristics combine to make Venus a captivating study in planetary science, showcasing the diversity of planetary behavior in our cosmic neighborhood. Olympus Mons stands out as the largest known volcano in the solar system, towering roughly 22 kilometers high, which is nearly 3 times the height of Mount Everest. Its massive shield structure spans approximately 600 kilometers in diameter, making it broader than the entire state of Arizona. This immense size is a consequence of the unique volcanic activity that has taken place on Mars over billions of years. The formation of Olympus Mons can be attributed to the type of volcanic activity that has occurred there. It is classified as a shield volcano, which is characterized by low viscosity lava that can flow great distances. Unlike Earth, where tectonic plates can inhibit the growth of volcanoes, Mars has a relatively static crust. This allows eruptions at Olympus Mons to continue for extended periods without being interrupted by tectonic movement, contributing to its enormous size. The continual buildup of lava flows over time has resulted in the gentle slopes and vast area that this volcano covers. Another fascinating aspect of Olympus Mons is its caldera, a large depression at its summit formed by the collapse of the volcano after massive eruptions. This caldera is about 80 kilometers wide and features several overlapping craters, indicating multiple phases of volcanic activity. The presence of these features demonstrates the long volcanic history of Olympus Mons and provides insight into the dynamics of volcanic processes on Mars. The study of Olympus Mons not only highlights the geological processes at play on Mars, but it also invites comparisons with terrestrial volcanoes. This giant volcano serves as a testament to the planet's rich geological past, showcasing the extraordinary phenomena that can occur in our solar system when conditions allow for unimpeded volcanic activity. The prevailing theory regarding the Moon's formation is known as the giant impact hypothesis. This suggests that around 4.5 billion years ago, shortly after Earth formed, a Mars-sized body, often called Theia, collided with the young Earth. The impact was so intense that it ejected a significant amount of material into space. Over time, this debris coalesced under its own gravity to form what we now know as the Moon. The Moon holds great significance for life on Earth for several reasons. Firstly, its gravitational pull plays a critical role in stabilizing Earth's axial tilt. This tilt affects the planet's climate and contributes to the changing seasons. Without the Moon's stabilizing presence, Earth could experience more severe variations in climate, which would greatly impact the development and sustainability of life. Additionally, the Moon influences ocean tides, creating regular rhythmic movements of water that are essential for coastal ecosystems. Tides help distribute nutrients in the ocean and create a dynamic environment that supports various forms of marine life. These tidal patterns also have implications for terrestrial life, as they can affect weather and climate systems on land. Moreover, the Moon has served as a vital point of reference for humanity throughout history. Its phases have guided agricultural practices, navigational methods, and timekeeping. The Moon's presence has also inspired cultural and scientific advancements, fueling curiosity and exploration. The formation of the Moon through a cataclysmic impact has led to its essential role in supporting life on Earth, affecting everything from climate stability to ecological systems. Its presence continues to be felt not only in our natural world, but also in human culture and exploration. The solar system presents a remarkable variety of temperature extremes, encompassing both scorching heat and frigid cold. When considering the highest temperatures, the planet Venus takes the lead, boasting surface temperatures that can reach approximately 460 degrees Celsius. This scorching heat is primarily the result of an intense greenhouse effect, where thick clouds of carbon dioxide trap heat very effectively, making Venus the hottest planet, even more so than Mercury, which is closer to the Sun. On the opposite end of the temperature spectrum, the coldest natural temperatures in the solar system have been recorded on Triton, Neptune's largest moon. Triton has an average surface temperature of around -273 degrees Celsius. This frigid environment is further accentuated by Triton's thin atmosphere and its distance from the Sun. The extreme cold on Triton results in the condensation of gases like nitrogen onto the surface, creating a unique and icy landscape. Another contender for extreme cold is the dwarf planet Pluto. While often debated whether to classify it as a planet, Pluto experiences surface temperatures that can plummet to about -278 degrees Celsius. Its atmosphere is thin and primarily composed of nitrogen, which can freeze onto the surface during its long orbit around the Sun, creating vast nitrogen ice plains. Exploring these extremes gives us valuable insights into the conditions that can exist in our solar system. While the planets and moons exhibit remarkable differences, they showcase the incredible diversity of environments that exist beyond our own world, furthering our understanding of celestial phenomena and the potential for life in various conditions. Pluto was reclassified from a planet to a dwarf planet in 2006 by the International Astronomical Union. This decision stemmed from the need for a clearer definition of what constitutes a planet. The reclassification highlighted that Pluto did not meet all the criteria established for full planetary status. To be classified as a planet, an object must meet 3 specific criteria. It must orbit the Sun, it must be spherical in shape due to its own gravity, and it must have cleared its orbital neighborhood of other debris. While Pluto orbits the Sun and is spherical, it does not satisfy the 3rd criterion. Pluto shares its orbital zone with other objects of similar size in the Kuiper Belt, a region beyond Neptune filled with icy bodies and other dwarf planets. In light of this, Pluto is now classified as a dwarf planet. This category is meant for celestial bodies that are similar to planets, but do not fulfill all the conditions necessary to be deemed a full planet. The reclassification of Pluto sparked considerable debate and discussion in the scientific community and among the public. Many remain emotionally attached to Pluto as the ninth planet of our solar system. This change in classification reflects the evolving nature of astronomy and our understanding of celestial bodies. As new discoveries are made and our knowledge expands, the classifications may continue to adapt. Pluto remains an intriguing object of study, and its status as a dwarf planet has opened up new avenues of exploration about the characteristics and conditions of objects in our solar system. Our solar system is home to a fascinating array of moons, many of which exhibit bizarre and unique characteristics. One of the strangest is Europa, one of Jupiter's largest moons. Europa is particularly intriguing due to its smooth, icy surface, which conceals a vast ocean of liquid water beneath. This hidden ocean may harbor the conditions necessary for life, leading scientists to consider Europa one of the top candidates for extraterrestrial organisms within our solar system. Additionally, the surface shows signs of geological activity, including features that resemble ice plates drifting apart, suggesting a dynamic environment. Another remarkable moon is Enceladus, Saturn's sixth largest moon. Enceladus stands out because of its geysers that erupt plumes of water vapor and ice particles from its south polar region. These geysers are believed to originate from a subsurface ocean similar to Europa's, and the plumes have been confirmed to contain organic compounds, raising further questions about the potential for life. The presence of these geysers also contributes to Saturn's stunning E-ring, making Enceladus a key player in understanding both its parent planet and the possibilities of life beyond Earth. Triton, Neptune's largest moon, offers another set of intriguing features. Triton is unique because it has a retrograde orbit, meaning it moves in the opposite direction to Neptune's rotation. This unusual orbit suggests that Triton may have been captured by Neptune's gravity rather than having formed in place. The moon's icy surface displays geysers that erupt nitrogen gas, similar to those found on Enceladus, making it a dynamic and captivating body to study. These moons represent just a few examples of the strange and beautiful diversity found among the natural satellites in our solar system. Their unique characteristics prompt scientists to explore the complex interactions between celestial bodies and deepen our understanding of the potential for life beyond Earth. Each of these moons continues to intrigue researchers and deepen our appreciation of the wonders of the cosmos. The Kuiper Belt, a region of the solar system beyond Neptune, is thought to be home to a staggering number of objects. Estimates suggest that there could be as many as 100,000 objects larger than 100 kilometers across within this vast area, and that number escalates dramatically when considering smaller bodies, potentially reaching into the millions. The Kuiper Belt is composed of a variety of icy bodies, including dwarf planets, comets, and other celestial objects made primarily of frozen gases, rock, and dust. Some of the most notable inhabitants include Pluto, Haumea, and Makemake, each offering valuable insights into the formation and evolution of our solar system. The region is also rich in smaller objects that have yet to be thoroughly mapped or studied. The difficulty in precisely counting these objects lies in their distance from the Sun, which makes them faint and challenging to observe. As telescopes and observational techniques improve, astronomers continue to discover new objects and refine existing estimates. The ongoing exploration of the Kuiper Belt enhances our understanding of its complexity and the potential for studying the early solar system, as many of these objects are considered to be remnants from its formation. Understanding the Kuiper Belt expands our knowledge of the solar system's architecture and the processes that shaped it. The diverse range of objects found there provides a window into the conditions and materials that were present during the solar system's formation, making it a focal point for both observational and theoretical research. The collision of two neutron stars is one of the most violent and energetic events in the universe, heralded by a catastrophic explosion known as a kilonova. When these incredibly dense stars, each more massive than the Sun but only about 20 kilometers in diameter, spiral toward each other, they emit gravitational waves, which are ripples in spacetime that can be detected by observatories like LIGO. As the neutron stars approach one another, their gravitational pull intensifies, leading to increasingly strong tidal forces. Once they finally merge, the resulting explosion leads to the creation of an accretion disk made of neutron-rich material. This disk becomes extremely hot and can emit intense gamma-ray bursts, which are a short-lived but incredibly powerful form of radiation. The merger also produces heavy elements such as gold and platinum through a process called rapid neutron capture, or R-process nucleosynthesis. This outcome provides an explanation for the origins of some of the universe's heaviest elements, and scientists believe that a significant portion of these elements found on Earth may have been formed during such neutron star collisions. Overall, the collision of neutron stars not only results in spectacular cosmic displays, but also plays a crucial role in understanding fundamental processes in the universe. Observing these events allows astronomers to study the nature of gravity, the properties of neutron stars, and the synthesis of heavy elements, enriching our knowledge of the cosmos. Astronomers employ several methods to measure the distance to stars, with one of the most traditional and effective techniques being parallax. Parallax relies on the apparent motion of nearby stars against more distant background stars, as observed from different positions of Earth in its orbit around the Sun. By measuring the angle of this apparent shift over a 6-month period, astronomers can use basic trigonometry to calculate the distance to the star. This method is highly effective for stars that are relatively close, typically within a few hundred light-years from our planet. For stars that are farther away, astronomers use standard candles, a technique involving objects with known brightness. Cepheid variable stars are an excellent example of standard candles. Their luminosity varies in a predictable pattern, allowing astronomers to determine their distance by comparing their known brightness to their observed brightness from Earth. By utilizing this relationship, they can effectively gauge how far away these stars are, even if they reside in distant galaxies. Another approach involves using redshift, particularly for galaxies or groups of stars. When light moves away from us, its wavelength stretches, shifting towards the red end of the spectrum. By measuring this redshift, astronomers can determine how fast an object is moving away and, using Hubble's law, infer its distance. This method is crucial for gauging distances on a cosmological scale and understanding the expansion of the universe. Each of these techniques serves as a tool in an astronomer's toolkit, allowing for a multifaceted approach to measuring distances across vast cosmic landscapes. Collectively, they provide essential insights into the structure and scale of our universe. A pulsar is a highly magnetized, rotating neutron star that emits beams of electromagnetic radiation out of its magnetic poles. These incredible celestial objects are the remnants of massive stars that have undergone supernova explosions, collapsing under their own gravity into extremely dense spheres composed predominantly of neutrons. A typical pulsar can have a mass greater than that of the Sun, but be only about 20 kilometers in diameter, creating an environment with incredibly strong gravitational and magnetic fields. The apparent pulsing of a pulsar occurs due to the alignment of its magnetic field with its rotation axis, which is not perfectly aligned with its rotational spin. As the pulsar rotates, the beams of radiation sweep across the universe like lighthouse beams. If Earth lies within the path of these beams, we observe them as regularly spaced pulses in the light or radio waves emitted by the pulsar. The speed at which these pulses occur can vary widely. Some pulsars rotate several hundred times per second, creating remarkably regular intervals between pulses. One of the reasons pulsars are of significant interest to astronomers is their precise timing. The regularity of their pulsing allows for incredibly accurate measurements of time, making them useful tools for studying gravitational waves and testing theories of general relativity. Moreover, observing pulsars helps scientists understand extreme states of matter, as they provide valuable data on nuclear physics under conditions impossible to replicate on Earth. Ultimately, pulsars serve as cosmic beacons, offering insights not only into the life cycles of stars, but also into fundamental physics and the nature of the universe. As their pulses can be detected across vast distances, they continue to deepen our understanding of the cosmos. A star's mass is the primary factor that dictates its life cycle and eventual fate. Stars form from clouds of gas and dust, and the mass of the material that collapses under gravity to create a star plays a crucial role in determining how long the star will live and what will happen to it once it exhausts its nuclear fuel. For massive stars, typically those with masses greater than about 8 times that of the Sun, the journey is relatively short but dramatic. These stars burn through their hydrogen fuel at a significantly higher rate, leading to a quicker progression through the various stages of stellar evolution. After exhausting hydrogen, they will fuse heavier elements in their cores, creating elements such as helium, carbon, and iron. Eventually, when iron builds up, fusion ceases to release energy, resulting in core collapse and triggering a supernova explosion. This spectacular event may leave behind a neutron star, or if the original mass is sufficient, even collapse into a black hole. In contrast, stars with masses similar to or less than that of the Sun have a more protracted life cycle. After exhausting hydrogen in their cores, these stars will swell into red giants, and the outer layers will eventually be expelled, forming a planetary nebula. The remaining core will become a white dwarf, which will gradually cool and fade over billions of years. The different endings for massive and less massive stars highlight the influence of mass on stellar evolution. It shapes not only the length and intensity of a star's life, but also the types of elements that are produced and released into the universe. This process of nucleosynthesis contributes to the chemical richness of galaxies, providing the building blocks for new stars, planets, and ultimately life itself. Understanding these relationships deepens our knowledge of the cosmos and the intricate ways in which stellar dynamics shape the universe around us. The title of the largest known star in the universe is often given to Scuti, a red supergiant located in the constellation Scutum. This colossal star is estimated to be about 1,700 times the radius of our Sun. If Scuti were placed at the center of our solar system, its outer edges would extend past the orbit of Saturn, dwarfing the planets that revolve around our star. Red supergiants like Scuti are the final stage in a star's life cycle. They typically form when massive stars exhaust their nuclear fuel and undergo significant expansion and cooling. This transformation results in a star that can be both awe-inspiring in size and ultimately prone to dramatic stellar events, such as supernova explosions that can occur once their life cycles come to an end. The sheer size of Scuti highlights the diverse range of stellar dimensions in our universe, as many stars are far larger than what we encounter within our own solar system. The scale of these celestial giants can be hard to comprehend. While our Sun, a medium-sized star, measures about 1,400,000 kilometers in diameter, Scuti's impressive size serves as a reminder of the vastness of the cosmos and the immense variety of stars within it. Comparatively, if you consider the size of Earth as a grain of sand, our Sun would be like a beach ball, while Scuti would be equivalent to a large balloon. The study of massive stars like Scuti not only fascinates astronomers, but also provides critical insights into the processes of star formation and evolution. As we continue to explore the universe, new discoveries may even lead to the identification of stars that could rival or surpass Scuti, reminding us that the cosmos is full of surprises waiting to be uncovered. Brown dwarfs are fascinating astronomical objects that occupy a unique niche between the largest planets and the smallest stars. Often referred to as failed stars, these celestial bodies are not massive enough to sustain the nuclear fusion of hydrogen in their cores, which is the defining characteristic of true stars. A brown dwarf typically has a mass between 13 and 80 times that of Jupiter, meaning they are significantly larger than gas giants, yet still insufficiently massive to ignite stellar fusion. The process of formation for brown dwarfs is similar to that of stars, originating from clouds of gas and dust that collapse under gravity. However, once a brown dwarf forms, it never reaches the necessary internal pressure and temperature to initiate hydrogen fusion. Instead, they shine dimly by burning deuterium and lithium, which are isotopes of hydrogen, for a short period before gradually fading over time. Instead, they shine dimly by burning deuterium and lithium, which are isotopes of hydrogen, for a short period before gradually fading over time. This leads to an intriguing set of characteristics, as brown dwarfs are not hot like stars, but are not entirely cold and dark like planets. The temperature of a brown dwarf can range from around 1,000 to 2,000 degrees Celsius, which is much cooler than most stars. This cooler temperature means that brown dwarfs can emit infrared radiation, making them detectable by specialized telescopes. Their unique properties place them in the category of substellar objects, and they have stimulated ongoing discussions among astronomers regarding the definitions of stars and planets. The discovery and study of brown dwarfs have expanded our understanding of the diversity of objects in our universe. They challenge the traditional boundaries between stars and planets, prompting scientists to rethink how we classify celestial bodies. These enigmatic objects continue to provide insights into the processes of star formation and the evolution of our galaxy, revealing more about the myriad of worlds that exist beyond our solar system. Binary star systems consist of two stars that are gravitationally bound to each other, orbiting around a common center of mass. This relationship can lead to a variety of fascinating phenomena, depending on the characteristics of the two stars involved. In these systems, the stars can have different masses, sizes, and evolutionary stages, with interactions that can significantly impact their evolution and behavior over time. 2. There are two main types of binary star systems: close binaries and wide binaries. In close binaries, the two stars are in very close proximity, which can lead to significant interactions such as mass transfer from one star to the other. This process can create spectacular events like novae, when the material accumulated on the surface of the smaller star ignites in a burst of energy. In contrast, wide binaries are separated by much greater distances and have less significant interactions. They tend to evolve independently, though their gravitational influence can still affect each other over long periods. Binary star systems are surprisingly common. Estimates suggest that around half of all stars in our galaxy are part of a binary system in some form. This prevalence indicates that interactions between stars are a significant aspect of stellar evolution and dynamics. The study of binary stars is crucial for understanding stellar masses, distances, and compositions, as these systems provide valuable information that single stars alone cannot offer. The dynamics of binary star systems also play a vital role in the formation of complex astronomical phenomena, such as supernovae in binary populations, where one star in the system may exhaust its nuclear fuel and explode, potentially impacting the other star in ways that lead to further cosmic events. As astronomers continue to observe and study these intriguing systems, we gain deeper insights into the mechanics of how stars form, evolve, and interact throughout the vast universe. A hypernova is an exceptionally energetic explosion that occurs at the end of a massive star's life cycle, characterized by an output of energy that far exceeds that of a typical supernova. While both hypernova and supernova mark the demise of stars, especially those significantly larger than our Sun, hypernovae are believed to result from the collapse of stars with masses greater than about 30 solar masses. This immense energy release can be as much as 100 times greater than that of an ordinary supernova. The primary difference between a hypernova and a supernova lies in the energy released during the explosion and the mechanisms that drive each event. Supernovae are generally classified into two main types: Type 1, which occurs in binary systems when a white dwarf accumulates matter until ignition, and Type 2, which results from the core collapse of massive stars. Hypernovae, particularly those associated with long-duration gamma-ray bursts, often involve the formation of a black hole or a neutron star after the explosion, releasing powerful jets of high-energy gamma radiation along with the explosion. Hypernovae not only release tremendous energy but also eject large amounts of material into space. This ejected material plays a crucial role in enriching the surrounding environment with heavy elements created during the star's nuclear fusion processes. As these elements disperse into the interstellar medium, they contribute to the formation of new stars and planets, fueling the cosmic recycling process that drives the evolution of galaxies. Research into hypernovae continues to advance, leading to a greater understanding of their properties, mechanisms, and impact on the surrounding universe. These extraordinary events challenge our comprehension of stellar evolution and explosive phenomena, offering insights into some of the most energetic processes that occur in the cosmos. Detecting exoplanets, or planets that orbit stars outside our solar system, has become an exciting area of modern astronomy. Astronomers employ several techniques to identify these distant worlds, with two of the most prominent methods being the transit method and the radial velocity method. Each approach has its unique advantages and provides different insights into the properties of exoplanets. The transit method involves monitoring the brightness of stars over time. When a planet passes in front of its host star from our viewpoint, it blocks a small portion of the star's light, causing a temporary dip in brightness. By observing and measuring these periodic dips, astronomers can infer the presence of an exoplanet. This technique is particularly useful in large surveys, such as the Kepler Space Telescope mission, which has discovered thousands of exoplanets using this method. The depth and duration of the transit can also provide information about the planet's size and orbital period. The radial velocity method, also known as the Doppler spectroscopy technique, relies on detecting the wobble of a star caused by the gravitational pull of an orbiting planet. As the planet orbits, it exerts a slight gravitational tug on the star, causing the star to move in a small orbit of its own. This movement affects the star's light spectrum. When the star moves toward us, its light shifts to higher frequencies, and when it moves away, the light shifts to lower frequencies. By measuring these shifts in the star's spectral lines, astronomers can determine the presence of an exoplanet and estimate its mass and orbital distance. Additional techniques, such as direct imaging, allow astronomers to capture actual images of exoplanets by blocking out the star's light, allowing the faint light of an exoplanet to be seen. This method is particularly challenging due to the vast brightness differences between stars and their planets, but has successfully revealed several exoplanets directly. The search for exoplanets has not only increased our understanding of planetary systems beyond our own, but has also raised intriguing questions about the possibility of life elsewhere in the universe. As technology advances, astronomers continue to refine these techniques, leading to the discovery of more and more distant worlds, each with unique characteristics and potential for habitability. A magnetar is a type of neutron star that possesses an incredibly powerful magnetic field, making it one of the most magnetic objects in the universe. Neutron stars themselves form when a massive star undergoes a supernova explosion, leaving behind a compact core made almost entirely of densely packed neutrons. Despite their small size, typically only about 20 kilometers in diameter, neutron stars possess extraordinary gravitational and magnetic properties. What sets magnetars apart from regular neutron stars is their extraordinarily strong magnetic fields, which can reach strengths over 1,000 trillion Gauss. To put this in perspective, the magnetic field of an average refrigerator magnet is about 1,000 Gauss. The intense magnetic field of a magnetar is believed to arise from the processes that occur during the star's rapid rotation after its formation. When a neutron star spins rapidly, it can generate powerful magnetic fields, and under certain conditions, these fields can increase even further, creating the extreme conditions seen in magnetars. The intense magnetic fields of magnetars have significant effects on their surroundings and behavior. They can emit bursts of high-energy radiation, including X-rays and gamma rays, leading to incredibly energetic phenomena. These bursts can be so powerful that they can outshine entire galaxies, albeit only for a brief duration. The magnetosphere surrounding a magnetar is filled with energetic particles, and the dynamics of this magnetosphere can produce powerful pulsar-like emissions, giving magnetars their distinct patterns of radiation. Magnetars are not just curiosities, they provide important insights into fundamental physics and stellar evolution. Their extreme environments challenge our understanding of magnetism and the behavior of matter under such intense conditions. As astronomers study magnetars, they uncover secrets about the life cycles of stars, the nature of neutron matter, and the dynamics of the universe's most extreme magnetic fields. Estimates suggest that there are around 2 trillion galaxies in the observable universe. This staggering number comes from various surveys and observations conducted by powerful telescopes, such as the Hubble Space Telescope. These observations have revealed that the universe is teeming with an immense variety of galaxies, ranging from small, dwarf galaxies to massive spiral and elliptical galaxies. The presence of so many galaxies highlights the complexity and vastness of the cosmos. Each galaxy contains billions or even trillions of stars, along with numerous planets, nebulae, and other celestial objects. The diversity of galaxy types and structures contributes to the rich tapestry of the universe, providing scientists with valuable information about cosmic evolution, formation processes, and the nature of dark matter and dark energy. Recent studies have explored the potential number of galaxies using advanced techniques like deep field imaging, which captures light from some of the faintest and most distant galaxies. These findings have often led to surprise revelations, as astronomers continuously adjust their estimates to account for the immense scale of the universe, bringing the total of observable galaxies into the trillions. As our observational techniques improve and more powerful telescopes are developed, such as the James Webb Space Telescope, it is possible that even more galaxies will be discovered. This ongoing exploration reshapes our understanding of the universe and opens new avenues to investigate the fundamental questions about the nature of galaxies and their role in the cosmic narrative. The largest known structure in the universe is the Hercules Corona Borealis Great Wall, an enormous galactic supercluster complex that spans about 10 billion light-years across. This colossal structure was discovered through analysis of gamma-ray bursts and galaxy surveys, revealing a vast network of galaxies and galaxy clusters interwoven across an immense area of space. Galactic structures like the Hercules Corona Borealis Great Wall are formed by the gravitational attraction between matter in the universe. As galaxies and galaxy clusters are drawn to one another, they create large-scale formations that can stretch for immense distances. This particular structure contains multiple galaxy clusters and is interconnected by filaments of dark matter and gas, which are the building blocks of the universe's large-scale structure. The size of the Hercules Corona Borealis Great Wall challenges our understanding of cosmic scales. When considering that the observable universe is about 13.8 billion years old, the distances involved with such structures reveal the vastness of space and the complexity of its composition. The interactions and formations among galaxies at this scale provide significant insights into the nature of cosmic evolution, the distribution of matter, and the forces at work in the universe. As astronomers continue to survey the cosmos using advanced technologies, it is possible that even larger structures could be discovered. Each new finding prompts further contemplation about the distribution of galaxies and the underlying principles that govern the universe's evolution. The ongoing exploration of these immense structures continues to deepen our appreciation for the astonishing vastness and intricacy of the universe. Galaxies form and evolve through a complex series of processes that stretch over billions of years. The formation of a galaxy begins shortly after the Big Bang, when the universe was still in its infancy, and consists of the gradual accumulation of matter. Initially, small fluctuations in density within the primordial hydrogen and helium gas led to regions where matter began to clump together due to gravity. Over time, these areas grew denser, attracting more gas and dust and laying the groundwork for the formation of stars and galaxies. As these regions continued to collapse under their own gravity, they formed the first stars. These early stars played a crucial role in galaxy formation by producing heavier elements through nuclear fusion. When they reached the end of their life cycle, many of these stars exploded in massive supernova events, scattering these newly created elements throughout the surrounding space. This process enriched the interstellar medium with metals, which are essential for the formation of subsequent generations of stars and planets. As galaxies began to form, they underwent mergers and interactions with other galaxies. These gravitational encounters can significantly alter a galaxy's shape, size, and star formation activity. For example, when two galaxies collide, their gas can be compressed, triggering new waves of star formation. Such galactic mergers are thought to be common in the early universe and can lead to the formation of larger structures like elliptical galaxies from smaller spiral galaxies. Over time, galaxies continue to evolve through various processes, including star formation, supernovae feedback, and interactions with neighboring galaxies. This ongoing evolution plays a key role in determining a galaxy's morphology and the distribution of its stars, gas, and dust. Therefore, the story of galaxies is dynamic, shaped by both internal processes and external influences, leading to a rich variety of galaxies observed today, from stunning spirals to massive elliptical forms. As researchers study these processes, they gain deeper insights into the history of the universe and the complex tapestry of cosmic evolution. The Great Attractor is a massive gravitational anomaly located in the direction of the Centaurus and Hydra constellations. This region influences the motion of galaxies over vast scales, causing them to move toward it at significant velocities. It is part of a larger structure known as the Laniakea supercluster, which is a vast collection of galaxies, including our own Milky Way, that are all influenced by this gravitational pull. The Great Attractor is thought to be composed of a concentration of mass, including galaxies and clusters of galaxies, though much of this mass is obscured from our view by the Milky Way's dust and gas. It is estimated that the Great Attractor contains several thousand galaxies and is roughly 100 million light-years away from Earth. The region's exact nature and composition have been challenging to determine due to the dense cosmic material that intervenes. The gravitational attraction exerted by this large mass affects the motion of galaxies that are situated within its vicinity. Because galaxies are not uniformly distributed in the universe, areas with higher concentrations of mass, like the Great Attractor, create gravitational wells that draw nearby galaxies toward them. Observations show that several galaxy clusters, including the Norma cluster and the Centaurus cluster, are moving toward this enigmatic attractor and illustrate the influence of such large-scale structures on cosmic dynamics. Understanding the Great Attractor is essential for grasping the large-scale structure of the universe. It exemplifies the significance of gravitational interactions on cosmic scales, showing how galaxies and galaxy clusters are interconnected within the cosmic web. As astronomers investigate further, they unravel the complex relationships among galaxies and the forces shaping their movements through the vast expanse of space. Measuring the mass of a galaxy is a challenging but essential task for astronomers, as it provides insights into a galaxy's composition, evolution, and dynamics. One of the primary methods used to determine a galaxy's mass involves analyzing the motion of stars and gas within the galaxy. By observing the velocities of these components, astronomers can apply principles derived from Newtonian physics and gravitational dynamics. When astronomers study the motion of stars within a galaxy, they often measure their velocities using spectroscopy. As stars move, their light is affected by the Doppler effect, which shifts the light to longer or shorter wavelengths depending on whether the stars are moving away from or toward Earth. By determining these shifts, astronomers can calculate the velocities of the stars in various regions of the galaxy. Using these velocity measurements, They can then estimate the total mass of the galaxy using the laws of gravitation, which relate the speed of orbiting stars to the mass that is exerting the gravitational force. For galaxies that are too large or too distant to measure individual star motions, astronomers can also look at the motions of galaxy clusters or the overall dynamics of groupings of galaxies. By assessing how quickly galaxies orbit around a common center of mass within a cluster, they can make inferences about the total mass of the cluster, including the contributions from both visible matter, like stars and gas, and dark matter, which does not emit light and is challenging to detect directly. Another valuable method for measuring galaxy mass involves gravitational lensing. This phenomenon occurs when a massive object, such as a galaxy or cluster of galaxies, bends the light from distant background objects. By studying the amount of distortion of the background light sources, astronomers can infer the mass of the foreground galaxy or cluster, as the degree of bending is directly related to the mass of the object causing the gravitational lensing. These various techniques allow astronomers to create a more complete picture of a galaxy's mass, which is crucial for understanding its formation, structure, and behavior within the broader context of the universe. By piecing together these mass measurements, scientists gain essential insights into the role galaxies play in cosmic evolution and the nature of dark matter that pervades the universe. Galaxy clusters are vast collections of galaxies bound together by gravity, making them the largest known gravitationally bound structures in the universe. These clusters can contain anywhere from a few dozen to thousands of galaxies, along with significant amounts of hot gas and dark matter. Galaxy clusters play a critical role in cosmic evolution as they serve as the foundational elements of the large-scale structure of the universe. Interactions between galaxies within clusters occur regularly due to the dense environment in which they reside. As galaxies pass close to one another, gravitational forces can lead to a variety of outcomes, including galaxy mergers, tidal interactions, and the stripping of gas and stars. Such interactions can trigger bursts of star formation when gas clouds are compressed, or they can lead to the formation of larger, more massive galaxies. These processes, called galactic cannibalism, often see larger galaxies growing by absorbing their smaller neighbors. On a larger scale, galaxy clusters themselves can also interact with one another. When clusters collide, they can create immense shock waves, compressing gas and leading to increased star formation in the member galaxies. These mergers often result in complex dynamics, with clusters exchanging members and merging into even larger structures. During such events, the interaction of dark matter plays a significant role. While normal matter, like gas and stars, interacts electromagnetically, dark matter interacts primarily through gravity and can create distinct observational effects. One notable phenomenon related to interacting galaxy clusters is the creation of large filamentary structures of galaxies linked by cosmic filaments of dark matter and gas, forming a web-like structure observed in the universe. These interactions continue to shape the evolution of both clusters and the individual galaxies within them, influencing galaxy morphology and the overall distribution of matter in the universe. Studying galaxy clusters and their interactions provides astronomers with valuable insights into the history and evolution of the universe. As these structures grow and merge over billions of years, they illustrate the dynamic nature of cosmic evolution, revealing the interconnectedness of galaxies and the forces that govern their behavior. Supermassive black holes, those with masses ranging from millions to billions of solar masses, reside at the centers of most large galaxies, including our Milky Way. Their presence has profound effects on the galaxies in which they exist, influencing various aspects of their structure, dynamics, and evolution. One of the primary ways supermassive black holes affect their host galaxies is through gravitational influence. The intense gravitational pull of a supermassive black hole can significantly shape the orbits of stars and gas in the central regions of the galaxy. This gravitational interaction can help regulate the movement and distribution of stars, leading to the formation of dense stellar clusters around the black hole and shaping the overall morphology of the galaxy. Additionally, supermassive black holes can have a dramatic impact on star formation through mechanisms referred to as feedback processes. When matter falls into a black hole, it often forms an accretion disk, where it heats up due to friction and releases enormous amounts of energy, often in the form of X-rays and other high-energy radiation. This energy can drive powerful winds and outflows, heating and expelling gas away from the central region. This feedback inhibits star formation in the vicinity of the black hole, as it prevents the accumulation of gas necessary for the birth of new stars. Such processes are crucial in regulating the growth of the galaxy over time. Furthermore, the energy output from supermassive black holes can lead to large-scale phenomena, such as active galactic nuclei, where the black hole actively accretes material. This process can create jets of particles that extend far beyond the host galaxy, influencing the intergalactic medium and even affecting the evolution of neighboring galaxies by altering gas flows. Ultimately, the relationship between supermassive black holes and their host galaxies is one of mutual influence. As galaxies evolve, they likely affect the growth and activity of the black holes, and vice versa. This intricate interplay plays a significant role in shaping the characteristics of galaxies, ultimately influencing their evolution and the formation of structures in the universe. Understanding these dynamics provides crucial insights into galaxy formation and the life cycle of celestial bodies. The Fermi bubble is a pair of enormous lobes of high-energy gamma-ray emissions that extend above and below the plane of our Milky Way galaxy. These structures are thought to represent outflows of hot gas and cosmic rays generated by the energetic processes within the galaxy, possibly associated with the supermassive black hole at the center of the Milky Way, known as Sagittarius, a star. Each lobe of the bubble stretches about 25,000 light-years in height, making them one of the most striking features of the galactic center. The discovery of the Fermi bubble was made possible through data collected by the Fermi Gamma Ray Space Telescope, which was launched in 2008. The telescope was designed to observe cosmic gamma rays across a wide range of energy levels. During its surveys of the sky, scientists observed unexpected gamma ray emissions emanating from the galactic center region, revealing the symmetrical lobes that extend into the surrounding space. Subsequent studies suggested that the Fermi bubbles are filled with high-energy particles and magnetic fields. Various theories have been proposed to explain their formation, with one possibility being that they result from the past outbursts of the supermassive black hole or from powerful star formation events that can accelerate particles to very high energies. Additionally, interactions between cosmic rays and the interstellar medium could contribute to the observed emissions. The Fermi bubble's discovery has opened up new avenues for understanding the dynamics of our galaxy and the processes that govern its evolution. By investigating these massive structures, astronomers gain insights into the relationship between supermassive black holes, star formation, and the surrounding environment. The Fermi bubble serves as a fascinating example of how high-energy astrophysics can reveal the complex activities occurring within our galaxy and the broader universe. Mapping the distribution of dark matter in galaxies is a key focus in astrophysics, as dark matter constitutes a substantial portion of the universe's total mass. Although dark matter does not emit, absorb, or reflect light, astronomers have developed several methods to infer its presence and distribution based on its gravitational effects. One of the primary techniques used to map dark matter is gravitational lensing. This phenomenon occurs when the gravity of a massive object, such as a galaxy or galaxy cluster, bends the light from more distant background objects like galaxies. By studying the amount of distortion in the images of these background galaxies, astronomers can estimate the mass of the foreground object, allowing them to infer the distribution of dark matter. Strong lensing, which results in significant distortions and features like Einstein rings, provides particularly detailed information about the underlying mass distribution. Another important method involves studying the rotational dynamics of galaxies. By observing the rotation curves of spiral galaxies, astronomers can measure the velocities of stars and gas at various distances from the galaxy's center. According to Newtonian gravity, the rotation speeds should decrease with distance if only visible matter were present. However, many galaxies show flat rotation curves, suggesting that there is significantly more mass present than what can be accounted for by the visible matter alone. This discrepancy indicates the existence of dark matter halos surrounding galaxies, which extends far beyond their visible boundaries. Additionally, astronomers use simulations and computational models to understand how dark matter interacts with normal matter within galaxies. By comparing observed galaxy structures and motions with model predictions that include different distributions of dark matter, they can refine their understanding of its properties and distribution. Finally, cosmic simulations of large-scale structure formation also help map dark matter. These simulations use the laws of physics to study how dark matter evolves over time and how it influences the formation of galaxies and clusters, creating a comprehensive picture of dark matter's role across the universe. Through these various approaches, astronomers are gradually piecing together a clearer picture of dark matter's presence and distribution within galaxies, leading to a deeper understanding of this elusive component of the universe that shapes the structures we observe today. The cosmic web is a vast and intricate structure that is often described as the largest scale of the universe's arrangement. Imagine it as a delicate fabric woven from clusters of galaxies, filaments, and voids. This web-like structure emerges from the gravitational attraction between matter, influencing the distribution of galaxies and providing a framework for how they connect and interact across the cosmos. At the heart of the cosmic web are massive clusters of galaxies, which serve as the nodes. These clusters are surrounded by long, thin filaments made up of dark matter and gas, threading through space and linking various clusters to one another. Between these filaments lie vast voids, regions where very few galaxies exist. This delicate balance of filaments and voids creates a dynamic environment where galaxies can grow and evolve as they are pulled towards higher density areas. Understanding the cosmic web enhances our insight into the formation and evolution of galaxies over billions of years. Galaxies do not exist in isolation. They inhabit a network that can affect their growth and behavior. The gravitational pull within the filaments can funnel gas into galaxies, fueling star formation and impacting their evolution. This interconnectedness also explains phenomena such as galactic mergers, where galaxies are drawn together, contributing to their growth and altering their shape and composition. Through cosmic surveys and innovative observational techniques, scientists have been able to map the cosmic web and study its properties. Observations suggest that around 80% of the universe's mass is made up of dark matter, which is a significant contributor to the structure of the cosmic web. By piecing together the properties of this network, researchers gain crucial insights into the history and fate of the universe, revealing how everything is bound together in an expansive, interconnected tapestry. Falling into a black hole is one of the most fascinating and extreme scenarios in astrophysics. As you approach the black hole, you would experience a phenomenon known as spaghettification. This occurs due to the immense gravitational field gradient near a black hole. If your feet were closer to the black hole than your head, gravity would pull your feet much more strongly than it pulls your head, stretching you into an elongated shape similar to spaghetti. This extreme tidal force would be relentless and would continue to increase as you got closer. Crossing the event horizon, the point of no return surrounding a black hole, is a critical moment. Once you pass this boundary, escape becomes impossible, even for light. In theory, you would not experience anything particularly strange upon crossing the event horizon itself. According to the principles of general relativity, an outside observer would see you freeze at the edge, while you would continue your journey inward, unaware of the fate that awaited you. This creates a fascinating paradox between the perspectives of an observer at a safe distance and that of the falling object. As you venture deeper into the black hole, the environment becomes increasingly hostile. Inside, the laws of physics as we know them begin to break down. Theoretically, all the mass of the black hole is concentrated at a singularity, a point of infinite density where our current understanding of physics ceases to be applicable. What happens at this singularity remains one of the biggest mysteries in modern physics. Some theories suggest that the fabric of space-time is fundamentally altered, and the concept of time itself could behave strangely. Ultimately, falling into a black hole leads to the destruction of any object that ventures too close, as the forces at play are unlike anything we experience on Earth. This exploration not only deepens our understanding of gravity and space-time, but also prompts questions about the fundamental nature of the universe and the limits of human knowledge. The study of black holes continues to challenge scientists to reconcile different theories of physics and to unlock the secrets hidden within these enigmatic cosmic phenomena. Supermassive black holes are colossal entities lurking at the centers of most, if not all, galaxies. Their formation is still a topic of active research, but several theories provide valuable insights into how these gigantic structures come into existence. One prevailing theory is that supermassive black holes formed from the direct collapse of massive gas clouds in the early universe. During the first few 100 million years after the Big Bang, vast amounts of gas collapsed under gravity, creating dense regions that could become the seeds of black holes. As these nascent black holes formed, they began to grow rapidly by accreting surrounding gas and merging with other black holes. The process is driven by the immense gravitational pull, attracting matter from the surrounding area toward the black hole. This accretion of material not only allows for growth, but also leads to the release of significant amounts of energy, which can result in the formation of active galactic nuclei, some of the brightest objects in the universe that emit energy across the electromagnetic spectrum. Another key aspect in the formation of supermassive black holes involves galaxy mergers. When galaxies collide, their central black holes may be drawn together and eventually merge, forming a more massive black hole. The dynamics of these collisions can funnel gas and stars inward toward the center of the galaxy, enhancing the black hole's growth. These interactions can lead to a dramatic increase in the black hole's mass, further establishing its central role within the galaxy. Recent research also suggests the possibility of primordial black holes, which could have formed in the early universe through fluctuations in density before stars and galaxies existed. If these primordial black holes existed, they might have provided another avenue for the masses observed in supermassive black holes today. As scientists continue to study the evolution of galaxies and black holes, the understanding of how these behemoths form and influence their galactic environments remains a captivating frontier in astrophysics. Hawking radiation is a groundbreaking concept proposed by physicist Stephen Hawking in 1974. The idea arises from the complex interplay of quantum mechanics and general relativity in the extreme environment surrounding black holes. According to Hawking's theory, black holes are not entirely black. Instead, they can emit radiation due to quantum fluctuations occurring just outside the event horizon. This radiation is a result of particle-antiparticle pairs that spontaneously form in the vacuum of space. Typically, these particle pairs annihilate each other almost immediately. However, if this occurs near the event horizon of a black hole, one member of the pair may fall into the black hole while the other escapes. The escaping particle becomes Hawking radiation. From the perspective of an outside observer, this radiation can appear as a form of thermal radiation, leading to the conclusion that the black hole loses mass as it emits Hawking radiation. Over incredibly long timescales, this process could potentially lead to the evaporation of the black hole itself, ultimately reducing its mass to zero. This concept has profound implications for our understanding of black holes and the nature of information in the universe. One of the most debated issues in theoretical physics is the fate of information that falls into a black hole. If black holes eventually evaporate due to Hawking radiation, the question arises, What happens to the information contained within the matter that fell into them? This dilemma, often referred to as the black hole information paradox, challenges the fundamental principles of quantum mechanics and has sparked extensive discussions among physicists. Hawking radiation not only offers insights into the long-term evolution of black holes, but also bridges several critical areas of modern physics, including thermodynamics, quantum theory, and cosmology. Its study continues to inspire new approaches to understanding the interplay of these fundamental concepts and the nature of the universe itself, as researchers strive to reconcile the theories of gravity with quantum mechanics. Gravitational waves are ripples in spacetime generated by the acceleration of massive objects, such as merging black holes or neutron stars. These waves were first predicted by Albert Einstein in 1915 as a part of his general theory of relativity, which describes how massive objects warp the fabric of spacetime. When such objects move, they create perturbations in this fabric that traveling waves can propagate through, much like a pebble creates ripples on the surface of a pond. Gravitational waves carry energy away from their source and travel at the speed of light. They dramatically stretch and compress spacetime as they pass through, creating variations in distance between objects. While these effects are incredibly small, they can be detected, as evidenced by numerous groundbreaking discoveries in astrophysics. The detection of gravitational waves is achieved through highly sensitive instruments known as interferometers. The most notable of these is the Laser Interferometer Gravitational Wave Observatory, commonly referred to as LIGO. LIGO consists of two facilities in the United States that are separated by several thousand kilometers. Each facility has two long arms arranged in an L shape. When a gravitational wave passes through the detector, it causes minute changes in the lengths of these arms, leading to a pattern of interference in the laser beams used for measurement. To achieve the necessary sensitivity for detecting these faint signals, LIGO employs sophisticated techniques, including laser technology, vacuum systems to eliminate air fluctuations, and isolation systems to minimize vibrations from the environment. The success of LIGO in detecting gravitational waves made monumental headlines in 2015 when it observed the waves created by the merger of two black holes located more than 1 billion light-years away. This groundbreaking achievement opened up a new realm of astronomy, allowing scientists to study cosmic events that were previously invisible. Detecting gravitational waves not only enhances our understanding of the universe's most violent phenomena, but also provides a fresh perspective on fundamental questions about the nature of gravity and spacetime. As technology continues to advance, new detectors are being developed, promising even greater sensitivity and the potential for unprecedented discoveries in the field of astrophysics. A white hole is a theoretical cosmic entity that acts as the opposite of a black hole. While black holes are regions of spacetime from which nothing can escape due to their immense gravitational pull, white holes are believed to expel matter and energy, allowing nothing to enter. Essentially, a white hole would be a one-way exit from spacetime, emerging from an event horizon and ejecting matter as opposed to trapping it. The concept of white holes arises from the equations of general relativity, just as black holes do. When thinking about black holes, scientists often explore what might exist on the other side of the event horizon. In theory, a white hole could be described as an extension of a black hole's properties, with some interpretations suggesting that every black hole has a corresponding white hole in a parallel universe or distant region of spacetime. This connection raises intriguing possibilities about the universe's structure and nature. Despite the mathematical underpinnings, empirical evidence for white holes remains elusive. Some scientists speculate that white holes could play a role in cosmic phenomena, such as gamma-ray bursts or the creation of new universes, which may be linked to black holes. In this scenario, matter absorbed by a black hole could emerge from a white hole in another part of the universe or in a different dimension. This idea has fueled hypotheses regarding the behavior of black holes and cosmological models. The challenges in probing the existence of white holes stem from their inherently elusive nature, as their defining feature is to prevent any observation of their interiors. Further complicating matters, the laws of thermodynamics suggest that white holes would be unstable and quickly fade away. While the realm of theoretical physics thrives on speculation, the debate surrounding white holes encourages continued exploration into the mysteries of the universe, pushing the boundaries of our understanding of gravity, space-time, and the cosmos as a whole. Black holes exert a profound influence on both time and space due to their immense gravitational fields. According to Einstein's general theory of relativity, massive objects like black holes curve the fabric of space-time around them. This distortion results in a unique effect. The stronger the gravitational pull, the slower time passes relative to an observer at a distance. As you approach a black hole, this time dilation becomes increasingly pronounced, leading to fascinating consequences for anyone venturing near. For an observer watching someone fall into a black hole, it would appear as though time for that person slows down significantly as they near the event horizon, the boundary beyond which escape becomes impossible. The observer would perceive their companion almost frozen in time, never quite crossing that threshold. Meanwhile, for the individual falling in, they would experience time as usual until reaching the event horizon, where the nature of reality begins to shift dramatically. In addition to altering the passage of time, black holes can also warp space itself. They create a steep gravitational gradient that can affect the trajectories of objects nearby. This effect can lead to fascinating orbital behaviors, where stars or gas clouds can spiral into the black hole, while others might be flung into new, unpredictable paths. Such dynamics play a critical role in how matter behaves in the environments around black holes, influencing the formation of accretion disks, a swirling mass of gas and dust that spirals into the black hole. Moreover, black holes can even create a phenomenon known as gravitational lensing. As light from distant stars passes near a black hole, the immense gravity bends the light, causing the images of those stars to warp or multiply. This effect not only allows astronomers to observe distant objects that might otherwise be hidden, but also serves as a visual testament to the incredible power of black holes in bending the very fabric of space-time. The interplay between black holes, time, and space thus opens new avenues for understanding our universe and challenges our perception of reality at its most fundamental level. The Event Horizon Telescope is a groundbreaking global network of radio telescopes designed to capture images of black holes. By combining observations from multiple telescopes around the world into what is known as very long baseline interferometry, this ambitious project creates an Earth-sized virtual telescope with the sensitivity required to observe the faint signals emitted from the regions surrounding a black hole. This innovative approach enables astronomers to study celestial bodies that are otherwise too distant and too dim to be seen individually. The first historic image captured by the Event Horizon Telescope was of the black hole located at the center of the galaxy Messier 87, a supergiant elliptical galaxy about 53 million light-years away from Earth. This momentous achievement, announced in April 2019, marked a significant milestone in astrophysics, as it provided the first direct visual evidence of a black hole's presence. Prior to this, black holes had only been inferred through indirect evidence, such as their effects on nearby stars and gas. To create the image, the Event Horizon Telescope collected data over a week in April 2017, using 8 radio observatories situated across the globe. The observations focused on the region surrounding the black hole's event horizon, which emits radio waves due to the intense gravitational forces at play. The data collected was then processed and synthesized using complex algorithms to produce a single image, revealing a bright ring of light that encircled a dark center. This dark region represented the shadow of the black hole, surrounded by glowing material that the black hole's gravity bent and illuminated. The image of the black hole not only provided confirmation of theoretical predictions made by scientists, but also opened the door to further studies concerning black hole physics. It allows researchers to test aspects of general relativity under extreme conditions and to explore how matter behaves in the presence of such intense gravitational fields. The success of the Event Horizon Telescope stands as a testament to international collaboration in scientific research, providing a unique glimpse into one of the universe's most enigmatic structures and furthering our understanding of the nature of black holes. Astronomers have developed various innovative methods to study black holes, despite the fact that these enigmatic objects cannot be seen directly due to their profound gravitational pull, which prevents light from escaping. Instead, researchers focus on the effects that black holes have on surrounding matter and their environments. One of the primary methods involves observing the behavior of stars and gas clouds in the vicinity of a black hole. By analyzing the orbits of nearby stars, astronomers can infer the presence of a black hole and estimate its mass. For instance, the famous supermassive black hole at the center of our Milky Way galaxy, known as Sagittarius A star, was identified by tracking the motions of stars orbiting it at high velocities. Another significant technique used to study black holes is the examination of accretion disks. As matter from surrounding space, such as gas or dust, falls into a black hole, it forms a rapidly rotating disk that spirals inward. The intense gravitational forces and friction in the disk cause it to heat up, emitting radiation across various wavelengths, particularly in the X-ray spectrum. Observing this X-ray emission allows astronomers to gather valuable information about the properties of the black hole and its accretion process. Space-based observatories, such as the Chandra X-ray Observatory, provide essential data on these high-energy emissions. Gravitational waves also offer a novel avenue for studying black holes. When black holes collide or merge, they create ripples in space-time known as gravitational waves. Instruments like the Laser Interferometer Gravitational Wave Observatory have detected these waves, enabling scientists to gather information not only about the black holes themselves, but also about the events leading to their merger. This emerging field, often referred to as gravitational wave astronomy, has expanded our understanding of the universe and opened new avenues for exploring black hole properties. Finally, the Event Horizon Telescope allows astronomers to image the surroundings of black holes, providing indirect visual evidence of their existence. By focusing on the light emitted by matter swirling around a black hole's event horizon, researchers can produce images that validate theoretical models of black holes and test predictions from general relativity. Together, these diverse approaches create a comprehensive toolkit for studying black holes, enhancing our understanding of these mysterious cosmic entities and their profound influence on the universe. Black holes come in various sizes, and they are generally categorized into different classes, including stellar mass black holes and intermediate mass black holes, each distinguished by their mass and formation processes. Stellar mass black holes typically form from the gravitational collapse of massive stars at the end of their life cycles. When a star exhausts its nuclear fuel, it can no longer counteract the force of gravity, leading it to collapse under its own weight. The resulting stellar mass black holes usually range from about 3 to several tens of solar masses, with the most common ones hovering around 5 to 20 solar masses. Intermediate mass black holes, on the other hand, occupy a mass range that bridges the gap between the smaller stellar mass black holes and the supermassive black holes found at the centers of galaxies. They are theorized to have masses between 100 and 100,000 solar masses, but they remain more elusive in terms of observation. The formation mechanisms for intermediate mass black holes are less understood, and they might form through different processes, such as the merger of multiple stellar mass black holes or the direct collapse of massive gas clouds in dense star clusters. These two categories of black holes are significant in studying the universe's structure and evolution. Stellar mass black holes are more commonly identified through their interactions with companion stars or by their X-ray emissions from accretion disks. In contrast, The detection of intermediate mass black holes poses more of a challenge, as they are not as easily identifiable through these methods. Observations of specific environments, such as star clusters or the centers of galaxies, have led to candidates being identified as potential intermediate mass black holes. The increase in understanding of black hole formation and the diversity in their sizes have important implications for astrophysics, particularly when it comes to exploring how galaxies and their central supermassive black holes evolve over time. Studying the differences between stellar mass and intermediate mass black holes can shed light on the intricate processes occurring in the universe and contribute to our understanding of cosmic history. Binary black hole systems consist of two black holes that are gravitationally bound to each other, orbiting around a common center of mass. These systems can form through various processes, including the remnants of massive stars in close proximity or through the mergers of stellar mass black holes in dense star clusters. The dynamics of binary black holes can be quite intricate, as they interact with one another and can influence the gravitational environment around them, shedding light on the nature of gravity and black hole physics. As binary black holes rotate around each other, they emit gravitational waves, ripples in spacetime that carry energy away from the system. The rate of energy loss increases as the black holes spiral closer together. Over time, this energy dissipation causes their orbits to shrink, leading to an increasingly rapid orbital motion. Eventually, when the black holes get close enough, they can merge into a single, more massive black hole. This merger releases an immense amount of energy, predominantly in the form of gravitational waves, and produces distinct signals that can be detected by gravitational wave observatories like LIGO and Virgo. The merger process is incredibly dynamic and can be described in several stages. Initially, as the black holes approach one another, they disrupt their surrounding environments, potentially accreting gas and generating energetic jets. Once they enter the final moments of their merger, they generate strong bursts of gravitational waves that carry information about their masses and spins. This event is marked by a peak of oscillations in the gravitational wave signals, allowing scientists to infer the properties of the resulting black hole. After the merger, the newly formed black hole may undergo a phase known as ring down, where it settles into a stable state, emitting further gravitational waves as it vibrates like a ringing bell. This ring-down phase helps researchers analyze the characteristics of the black hole, such as its mass and spin, applying principles from general relativity. Studying binary black hole systems and their mergers has vastly expanded our understanding of black hole behavior and the dynamics of gravitational interactions. The observations of these events offer insights into fundamental questions about the nature of gravity and space-time, as well as the underlying processes that govern the evolution of black holes and their interactions within galaxies. Each merger event captured by gravitational wave detectors represents a new opportunity to test the limits of our theories and deepen our knowledge of the universe. Dark energy is a mysterious form of energy that permeates all of space and is believed to be responsible for the observed acceleration of the universe's expansion. Although it comprises approximately 70% of the total energy density of the universe, its exact nature remains one of the most significant puzzles in cosmology. Unlike ordinary matter and dark matter, dark energy does not clump in the same way and appears to exert a repulsive force that drives galaxies apart, contrary to the gravitational attraction exerted by matter. The concept of dark energy emerged from observations made in the late 1990s when astronomers studying distant supernovae discovered that the expansion rate of the universe was not slowing down, as previously expected, but was actually accelerating. This unexpected behavior prompted a search for an explanation, leading to the introduction of dark energy as a potential solution. The most widely accepted explanation for dark energy is the cosmological constant, originally proposed by Albert Einstein in his field equations of general relativity. In this view, dark energy is a constant energy density that fills space uniformly and has a negative pressure driving the acceleration. The effects of dark energy are profound and far-reaching. As it continues to dominate the energy content of the universe, dark energy shapes the large-scale structure and evolution of the cosmos. Its influence can be observed in the distribution of galaxies, where structures that would otherwise be affected by gravitational clumping are instead pushed apart, allowing the universe to expand at an increasing rate. This acceleration means that, regardless of the gravitational forces that exist between cosmic objects, dark energy ultimately prevails, dictating the fate of the universe. The study of dark energy is at the forefront of contemporary astrophysics, as scientists seek to understand its properties and underlying mechanisms. Various observational initiatives, such as the Dark Energy Survey and the upcoming Euclid satellite mission, are designed to probe the universe's expansion rate and gather data on dark energy's behavior over time. Insights gained from these studies may not only illuminate the nature of dark energy, but also have profound implications for the ultimate fate of the universe, furthering our understanding of the cosmos and the fundamental forces at play. Gamma-ray bursts, often referred to as GRBs, are among the most energetic and mysterious phenomena in the universe, emitting intense bursts of gamma radiation that can last from milliseconds to several minutes. These explosive events are detected as brief flashes of gamma rays from distant galaxies and are believed to be caused by highly energetic processes involving massive celestial objects. The origins of GRBs can be categorized into two main types: long-duration bursts and short-duration bursts, each associated with different astrophysical events. Long-duration gamma-ray bursts, which typically last more than 2 seconds, are thought to occur during the collapse of massive stars into black holes. When a massive star exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. As the core collapses, it may produce narrow jets of material that are ejected at nearly the speed of light, creating the burst of gamma rays observed from Earth. This process is often linked to supernova explosions, where the core collapse not only leads to the formation of a black hole, but also emits powerful beams of energy. If these jets are pointed toward Earth, they can be detected as a gamma-ray burst. Short-duration gamma-ray bursts, lasting less than 2 seconds, are believed to result from the merger of compact binary systems, such as two neutron stars or a neutron star and a black hole. The gravitational interactions during these mergers create immense energy, resulting in the ejection of matter and the emission of gamma rays. This type of GRB is also associated with kilonovae, which occur when neutron stars collide and produce heavy elements through rapid neutron capture processes. The immense power of gamma-ray bursts makes them detectable across vast cosmic distances, allowing astronomers to study the early universe and the formation of elements. Observations of GRBs have provided vital insights into the life cycles of massive stars, the behavior of matter in extreme conditions, and the dynamics of neutron star mergers. Furthermore, studying these events helps to enhance our understanding of the fundamental processes that shape galaxies and the evolution of the cosmos. Each gamma-ray burst serves as a unique probe into the universe, illuminating the most extreme and energetic processes occurring in the depths of space. Cosmic rays are high-energy particles that travel through space and continuously bombard the Earth from all directions. They primarily consist of protons, but they can also include heavy nuclei, electrons, and gamma rays. The origins of cosmic rays remain a topic of scientific investigation, but it is widely believed that they are produced by a variety of astrophysical processes occurring in the universe. The journey of cosmic rays through space begins in energetic environments, such as supernova explosions, active galactic nuclei, and pulsars. Supernovae, for example, can accelerate particles to nearly the speed of light during the explosive death of a massive star. The shock waves generated by these cosmic explosions interact with surrounding material, leading to the acceleration of particles into the high-energy regime. In addition to supernovae, active galactic nuclei, regions surrounding supermassive black holes in galaxies, can also produce cosmic rays through processes associated with the accretion of material and energetic jets. Once generated, cosmic rays travel vast distances across the universe, influenced by magnetic fields present in interstellar and intergalactic space. As they move, their paths can become convoluted due to the bending effects of these magnetic fields, making it challenging to trace their origins directly. Despite this deflection, researchers can analyze cosmic rays that reach Earth and use their energy and composition to infer where they might have originated. High-energy cosmic rays in particular may be linked to specific sources, like supernova remnants or active galactic nuclei. The detection of cosmic rays on Earth involves specialized instruments and detectors that capture the secondary particles generated when cosmic rays interact with the Earth's atmosphere. These secondary particles create cascades, enabling scientists to study the energy and composition of the original cosmic rays. By observing the distribution and energy spectra of cosmic rays, researchers can gather insights into the processes and astrophysical phenomena responsible for their creation. The study of cosmic rays not only reveals information about high-energy astrophysical environments, but also contributes to our understanding of fundamental questions related to particle physics and the universe's evolution. The cosmic microwave background radiation, often referred to as the CMB, is a faint glow permeating the entire universe and is considered one of the most significant pieces of evidence for the Big Bang theory. This radiation is composed of microwave wavelengths and is a remnant from the early stages of the universe, specifically from approximately 380,000 years after the Big Bang. At this time, the universe had cooled sufficiently for electrons and protons to combine and form neutral hydrogen atoms. This process allowed photons to travel freely through space for the first time, marking what is known as recombination. The CMB is detected as a nearly uniform background radiation isotropically distributed across the sky. However, slight variations in temperature and density are present, which provide crucial insights into the universe's structure and evolution. These temperature fluctuations, or anisotropies, correspond to regions of varying density that eventually gave rise to galaxies and large-scale structures we observe today. By studying the characteristics of these fluctuations, astronomers can glean information about the initial conditions of the universe, the rate of its expansion, and the composition of matter. The detailed analysis of the CMB has revealed essential parameters of the universe, including its age, composition, and geometry. Measurements made by several observatories, most notably the Wilkinson Microwave Anisotropy Probe and the Planck satellite, have determined that the universe is about 13.8 billion years old and is composed of approximately 24% dark matter, 72% dark energy, and only 4% ordinary matter. The CMB also supports the theory of inflation, a rapid expansion of the universe that occurred just after the Big Bang, which helps to explain the uniformity observed in the CMB. Ultimately, the cosmic microwave background radiation serves as a vital tool for cosmologists, offering a window into the early universe and allowing for precise measurements that deepen our understanding of cosmic evolution. The study of the CMB not only confirms key aspects of the Big Bang theory, but also continues to inspire further research into fundamental questions about the nature of the universe and its ultimate fate. Fast radio bursts, often referred to as FRBs, are incredibly brief but exceptionally powerful bursts of radio waves from deep space. These mysterious phenomena last only a few milliseconds but can release energy equivalent to that produced by the entire sun in just a few seconds. Discovered in 2007, the first FRB appeared as a single pulse, and since then astronomers have identified hundreds more, some repeating their bursts while others remain singular events. The origins of these radio bursts are still largely unknown, contributing to their enigmatic nature. Some theories suggest that they may be linked to powerful astrophysical events, such as the collapse of massive stars or collisions between neutron stars. Other hypotheses propose that they could be signals from advanced extraterrestrial civilizations, though this idea remains speculative and unsubstantiated. One of the reasons FRBs are so perplexing is their extreme distances. Many of these bursts originate billions of light-years away, meaning their radio waves travel vast stretches of space before reaching Earth. As these signals make their journey, they encounter various cosmic materials, impacting their properties, and making it difficult for scientists to interpret their origins accurately. Further complicating the mystery is the fact that not all FRBs are the same. Some emit one-off pulses, while others repeat at unpredictable intervals. The study of FRBs is still in its infancy, but as technology advances and telescopes become more sensitive, researchers hope to uncover the secrets behind these captivating cosmic events, ultimately shedding light on the processes occurring in the universe. Astronomers study antimatter through a combination of theoretical predictions and observational techniques that utilize advanced technology. Antimatter consists of particles that are the counterparts of ordinary matter particles, such as positrons, the antimatter equivalent of electrons. When antimatter comes into contact with matter, the result is annihilation, releasing energy in the form of gamma-ray radiation. This unique signature provides a way for scientists to detect and study antimatter in the universe. One of the primary methods of detecting antimatter involves observing high-energy gamma rays emitted from regions of space where matter and antimatter may be interacting. Space-based telescopes such as the Fermi Gamma Ray Space Telescope monitor the sky for these gamma-ray bursts, helping scientists identify potential sources of antimatter like pulsars or regions around black holes. These observations can offer insights into the conditions that lead to the creation of antimatter in the universe. Additionally, researchers create antimatter in particle accelerators on Earth, allowing them to study its properties in controlled environments. While these experiments do not directly observe antimatter in space, they help scientists develop models and understand how antimatter behaves when conditions are replicated. This knowledge can then be applied to the cosmos, making it easier to interpret observational data. Another intriguing aspect of antimatter research is its role in the evolution of the universe. The asymmetry between matter and antimatter remains one of the biggest mysteries in physics. Observations of cosmic phenomena, combined with theoretical frameworks, can potentially explain why our universe appears to be predominantly matter-dominated, despite expectations that equal amounts of both should have been produced during the Big Bang. Understanding antimatter not only expands our knowledge of the cosmos, but also challenges the very foundations of modern physics. Cosmic inflation is a theory that proposes a rapid expansion of the universe during its first moments, specifically from about 10 to the minus 34 seconds to about 10 to the minus 32 seconds after the Big Bang. This swift expansion suggests that the universe grew exponentially, potentially increasing in size by a factor of at least 100 trillion times or even more. This incredible burst of growth occurred before galaxies, stars, and other large structures began to form, fundamentally shaping the cosmos we observe today. One of the significant implications of cosmic inflation is its ability to explain the uniformity of the universe. Observations reveal a surprising homogeneity in the cosmic microwave background radiation, the afterglow of the Big Bang. This radiation appears almost uniform in all directions, with only tiny fluctuations. In a universe that has expanded so rapidly, inflation stretches out any initial irregularities, smoothing out the fabric of space and allowing it to appear remarkably uniform over vast distances. Additionally, inflation helps account for the current structure of the universe. It suggests that the small variations in density present in the early universe were responsible for the formation of galaxies and clusters as gravity pulled matter together over billions of years. The theory supports the idea that these initial fluctuations originated from quantum fluctuations in the very early universe, magnified to cosmic scales during the period of inflation. The concept of cosmic inflation not only provides a framework for understanding the uniformity observed in the universe, but also fits well with other cosmological observations, such as the distribution of galaxies and the large-scale structure of the cosmos. This interconnectedness of phenomena reinforces the importance of inflation as a central piece in the puzzle of how our universe evolved from an incredibly hot and dense state into the vast expanse we study today. Gravitational lenses are a fascinating consequence of Einstein's theory of general relativity, which states that massive objects like galaxies or clusters of galaxies can bend the path of light traveling near them. When light from a distant object, such as a galaxy or quasar, passes close to a massive foreground object, the gravitational field of that foreground mass distorts the light, causing the distant object to appear magnified, distorted, or even duplicated. This effect is not only visually striking but also serves as a powerful tool for astronomers. Astronomers utilize gravitational lensing in various ways to study the universe. One of the primary applications is measuring the mass of the foreground objects causing the lensing effect. By observing the degree of distortion and magnification in the light from the background object, scientists can derive the mass of the lensing galaxy or cluster. This method is particularly valuable because it allows researchers to probe the mass distribution of dark matter, which does not emit light and cannot be directly observed. Gravitational lensing also helps astronomers amplify the light from very distant faint objects that would otherwise be too dim to study. As the light from these distant sources passes through a gravitational lens, it becomes easier to observe. This enhanced visibility has enabled scientists to identify and analyze some of the earliest galaxies formed in the universe, offering insights into galaxy formation and evolution during the early epochs. Moreover, gravitational lensing serves as a tool for mapping the distribution of dark matter in the universe. By observing how light bends around unseen matter, astronomers can create models of dark matter's influence on the cosmic structure. This research aids in addressing questions about the nature and properties of dark matter, which remains one of the greatest mysteries in contemporary astrophysics. Through gravitational lensing, scientists unlock secrets of the cosmos, improving our understanding of the universe's structure and the fundamental forces at play. The Great Void, also known as the Giant Void, is an enormous, relatively empty region of space that is notable for its lack of galaxies compared to more densely populated parts of the universe. This immense void stretches across hundreds of millions of light-years and is characterized by a dramatic underdensity of matter and cosmic structures. What makes the Great Void particularly intriguing is how it forces scientists to rethink theories about the distribution of galaxies and the large-scale structure of the cosmos. The discovery of the Great Void dates back to the early 1980s, when astronomers were conducting surveys of galaxy distributions. Through these surveys, which mapped the positions of galaxies in the nearby universe, researchers noticed large expanses of empty space devoid of the normal clustering of galaxies that was expected based on previous models of the universe's structure. This observation led to more extensive studies, confirming the existence of massive voids. Finally, the Great Void was studied in detail using data from various astronomical surveys, including the 2-micron All-Sky Survey and the Sloan Digital Sky Survey. By analyzing large-scale galaxy distributions in conjunction with 3-dimensional maps of the cosmos, astronomers identified this particular void, recognizing that it is surrounded by filaments of galaxies, typical of cosmic web structures. The existence of the Great Void challenges traditional models of cosmology, particularly regarding how galaxies formed and evolved over billions of years. It raises questions about the role of cosmic expansion and dark energy in shaping the universe. Additionally, studying such voids can provide insights into cosmic evolution and the distribution of dark matter, further enhancing our understanding of the universe. The Great Void serves as a vivid reminder of the universe's complexity and the myriad structures that continue to intrigue scientists. The ultimate fate of the universe is a topic of intense speculation and research, with several competing theories attempting to explain how the cosmos may evolve in the far future. One prominent theory is known as the Big Freeze or heat death, which posits that the universe will continue to expand indefinitely. As galaxies move away from one another, stars will eventually burn out, and the universe will become increasingly cold and dark, ultimately reaching a state of maximum entropy, where no thermodynamic free energy remains to sustain processes that increase entropy. Another possibility is the Big Crunch, a scenario where the expansion of the universe eventually halts and reverses due to gravitational attraction. This would lead to a contraction of all cosmic structures, pulling galaxies back together until everything collapses into an infinitely dense point, similar to the conditions of the original Big Bang. While current observations suggest that the universe is accelerating its expansion, the future could hold surprises, such as a new understanding of the nature of dark energy. A more recently discussed concept is the Big Rip, which proposes that the universe's expansion continues to accelerate due to dark energy's influence. In this scenario, the repulsive force of dark energy would grow stronger over time, eventually leading to a point where galaxies, stars, planets, and even atomic structures are torn apart. The universe would meet its end as matter is ripped apart at an accelerating rate. Additionally, some theories suggest the possibility of cyclical universes, where the universe undergoes endless cycles of expansion and contraction. This concept posits that after a big crunch, the universe could bounce back and experience a new Big Bang, repeating the cycle indefinitely. Each cycle may bring variations in the properties and structure of the universe, leading to an ever-evolving cosmic landscape. These theories reflect the profound mysteries still surrounding the universe, prompting ongoing investigation into its ultimate fate amidst the ever-changing cosmos. Space telescopes, like the James Webb Space Telescope, are designed to observe the universe from above Earth's atmosphere, while ground-based telescopes operate within that atmosphere. One of the primary advantages of space telescopes is their ability to avoid atmospheric interference. Earth's atmosphere can distort light, absorb certain wavelengths, and create varying levels of turbulence that can significantly hinder observations. By positioning telescopes in space, astronomers eliminate these barriers, allowing for clearer and more precise imaging and data collection. Another key difference lies in the range of wavelengths that these telescopes can observe. While ground-based telescopes are limited by atmospheric conditions, which block certain infrared and ultraviolet wavelengths, space telescopes can access a much broader spectrum, including infrared, which is crucial for studying cooler celestial objects like newly forming stars and distant galaxies. The James Webb Space Telescope, for instance, is specifically designed to observe in the infrared range, enabling it to peer through dust clouds and explore the early universe, where light has been redshifted due to the expanding universe. Additionally, space telescopes like James Webb can operate autonomously in the harsh environment of space. Equipped with advanced instrumentation, they can conduct long-duration observations without the interruptions typical of Earth-based observation attempts caused by weather, light pollution, or the day-night cycle. This capability allows them to focus on specific cosmic targets, gathering valuable data over extended periods without disturbance. Finally, the engineering and technology involved in space telescopes are vastly different. Space missions require extensive planning, precision manufacturing, and testing to ensure that the instruments can function in the vacuum of space with minimal maintenance. This complexity translates into high costs, yet the payoff is a significantly enhanced ability to explore the universe and address fundamental scientific questions about its origins and evolution. Through the combined efforts of both ground-based and space-based observations, astronomers continue to push the boundaries of our understanding of the cosmos. Sending humans to Mars presents a unique array of challenges that encompass technology, physiology, logistics, and psychological factors. One of the most significant hurdles is the vast distance between Earth and Mars, which can vary from about 55 million kilometers to over 400 million kilometers, depending on their positions in their respective orbits. This distance translates into travel times of 6 to 9 months or more, necessitating spacecraft capable of sustaining human life, providing life support, and protecting against radiation exposure from cosmic rays and solar radiation. Radiation is a major concern during such a long space journey. Without Earth's protective atmosphere and magnetic field, astronauts would be exposed to levels of radiation that could increase their risk of cancer and damage to their central nervous system. To mitigate these risks, NASA and other agencies are exploring various habitat designs and radiation shielding technologies to ensure crew safety during transit and while on the Martian surface. Another challenge involves the effects of microgravity on the human body. Prolonged exposure to such conditions can lead to muscle atrophy, bone density loss, and changes in vision and cardiovascular health. Researchers are investigating countermeasures such as exercise regimens and specialized diets to help maintain astronaut health during the mission. Additionally, careful planning is needed to manage the psychological stresses astronauts may face during a lengthy isolation away from Earth, which can strain team dynamics and individual well-being. Logistical challenges also pose significant difficulties, including the need for reliable life support systems, food production, and waste management. Crews must be able to produce oxygen, recycle water, and grow food in the Martian environment, which requires advances in technologies that focus on sustainability. Also, developing affordable and efficient transportation systems for both the journey to Mars and the return trip adds complexity to mission planning. Each of these challenges must be carefully addressed to ensure a successful human mission to Mars, laying the groundwork for future exploration of the Red Planet and beyond. Ion engines, also known as ion thrusters, are a type of electric propulsion that utilize ions to generate thrust. The basic principle involves ionizing a propellant, typically a noble gas like xenon, by stripping away electrons. This process creates positively charged ions, which are then accelerated using electric fields generated by grids within the engine. As these ions are expelled at high speeds, they produce thrust according to Newton's third law of motion, producing a relatively small yet continuous force that can propel a spacecraft over extended periods. One of the most significant advantages of ion engines is their remarkable efficiency. Compared to traditional chemical rockets, which burn fuel to produce thrust, ion engines use significantly less propellant to achieve the same change in velocity. This high specific impulse means that they can accelerate spacecraft gradually for long durations, saving fuel and enabling missions that would otherwise be unfeasible. The ability to operate for extended periods allows ion thrusters to build up extraordinary speeds over time, making them ideal for deep space exploration. Ion engines also produce less thrust than conventional engines, which makes them unsuitable for launching spacecraft from Earth's surface. However, they are perfect for maneuvering and travel once in space. They have successfully powered various missions such as NASA's Dawn spacecraft, which explored the asteroid belt, and the European Space Agency's Bepi Colombo mission to Mercury. These missions exemplify how ion propulsion supports ambitious exploration initiatives by allowing spacecraft to travel greater distances with reduced fuel requirements. As space agencies plan future endeavors to explore distant planets and beyond, the efficiency and capabilities of ion engines play a pivotal role. They promise a viable means for reaching targets like Mars or even the outer planets in our solar system, potentially enabling more complex missions that can operate beyond the limitations of current propulsion technologies. In the quest to unlock the mysteries of our solar system, ion engines represent a crucial advancement in our ability to explore the cosmos. The Voyager program, launched by NASA in 1977, consists of two spacecraft, Voyager 1 and Voyager 2, designed to explore the outer planets and the far reaches of our solar system. Both spacecraft were equipped with a suite of scientific instruments to gather data on planetary atmospheres, magnetic fields, and surfaces, as well as to capture breathtaking images of their targets. Voyager 2, launched first, visited all four gas giants, Jupiter, Saturn, Uranus, and Neptune, while Voyager 1 focused primarily on Jupiter and Saturn, making critical observations that expanded our understanding of these colossal planets and their moons. One of the major contributions of the Voyager missions was the wealth of information gathered about Ganymede and Europa, Jupiter's largest moons, and Titan, Saturn's largest moon. The data revealed that these icy moons could harbor subsurface oceans, raising intriguing questions about the potential for life beyond Earth. Voyager's discoveries reshaped our knowledge of the outer solar system and spurred further exploration of these intriguing worlds. Each spacecraft also provided valuable insights into the magnetic fields and ring systems of the giant planets. Voyager's encounter with Jupiter allowed scientists to study its intense radiation belts and complex magnetic environment, while the probe's observations of Saturn's rings revealed intricate structures and dynamics previously unknown. Voyager 2's flybys of Uranus and Neptune yielded groundbreaking data, including the discovery of new moons and rings, while also providing detailed information regarding their atmospheric dynamics and weather systems. Beyond the planetary encounters, the Voyager spacecraft have continued to provide insights as they journey into interstellar space. Voyager 1 became the first human-made object to enter this region in 2012, delivering valuable data about the heliosphere, the solar wind, and cosmic rays. The program has not only significantly enhanced our understanding of the outer solar system, but has also afforded a unique perspective on humanity's place in the cosmos. As the Voyagers continue their journey, their legacy of exploration and discovery paves the way for future missions and deepens our curiosity about the universe. Astronauts aboard the International Space Station, or ISS, rely on a carefully designed set of systems and protocols to ensure their survival in the harsh environment of space. One of the primary challenges they face is the absence of gravity. To mitigate the effects of microgravity, astronauts engage in regular exercise using specialized equipment such as resistance machines and treadmills with harnesses. This physical activity helps them maintain muscle strength, bone density, and cardiovascular health during their time in orbit. Life support systems play a critical role in sustaining crew members aboard the ISS. These systems provide breathable air, typically composed of 21% oxygen and 79% nitrogen, by recycling carbon dioxide exhaled by the astronauts and filtering it back into a usable form. Additionally, water is recycled through advanced filtration technologies, enabling astronauts to collect moisture from the air and reclaim wastewater from personal hygiene and food preparation. This efficient use of resources is vital for long-duration missions, since resupply opportunities are limited. Food is another essential aspect of life on the ISS. Astronauts consume specially prepared and packaged meals designed to provide the necessary nutrients while being lightweight and easy to store. The menu includes a variety of options, from freeze-dried fruits to thermostabilized entrees. Astronauts also adjust to eating in microgravity, using utensils that prevent food from floating away during meals, which ensures they can sustain a balanced diet without creating a mess. Maintaining mental well-being is equally important for astronauts during extended stays in space. They participate in regular communication with family and friends back on Earth, and often have access to movies, books, and games to entertain themselves during downtime. Crew members are also trained to handle potential emergencies, so that they are prepared for various situations, from equipment malfunctions to medical issues. Together, these elements create a carefully orchestrated environment that enables astronauts to thrive while conducting scientific research and experiments in the unique setting of the International Space Station. Space junk, also known as space debris, refers to non-functional and discarded objects orbiting Earth. This includes defunct satellites, spent rocket stages, fragments from collisions, and other remnants from past space missions. As the number of objects in orbit has increased dramatically since the dawn of space exploration, so too has concern about the potential risks associated with this debris. Currently, there are tens of millions of pieces of space junk, ranging from tiny paint flecks to larger, hazardous fragments, all of which pose various threats to operational spacecraft and the International Space Station. One of the primary reasons space junk is a growing concern is the phenomenon known as the Kessler syndrome. This theory suggests that if the density of objects in low Earth orbit becomes sufficiently high, Collisions between debris could create additional fragments, leading to a cascade effect. As debris collides and breaks apart, the resulting fragments could cause further damage to active satellites and spacecraft, increasing the likelihood of more collisions. This creates a dangerous environment for future missions and has the potential to complicate ongoing scientific and commercial activities in space. Moreover, as private companies and various nations plan to launch thousands of new satellites for communication, data collection, and other purposes, the risk of collisions escalates. Space traffic management has become essential as operators of satellites are tasked with monitoring potential conjunctions, requiring them to maneuver their assets to avoid impacts with debris. The challenge lies in accurately tracking and predicting the paths of thousands of particles, many of which are too small to be catalogued but still large enough to cause significant damage. Efforts are underway to address the growing problem of space junk through international cooperation and technological innovation. Proposed solutions include developing methods to capture and deorbit defunct satellites, creating guidelines for responsible satellite design and end-of-life disposal, and launching cleanup missions to remove larger debris. As humanity expands its presence in space, addressing the issue of space junk has become imperative for ensuring the long-term sustainability and safety of both current and future space activities. Mining asteroids has emerged as an exciting prospect for scientists and space entrepreneurs, driven by the potential to harness valuable resources found in these celestial bodies. Most asteroids are rich in metals such as nickel, iron, and cobalt, as well as essential materials like water and rare earth elements. Plans to mine asteroids involve a combination of advanced technologies, robotics, and space exploration strategies aimed at extracting these resources efficiently and sustainably. One of the first steps in asteroid mining is identifying suitable targets. Scientists utilize telescopes and spacecraft to survey near-Earth asteroids, assessing their composition, size, and proximity to Earth. Various methods, including spectroscopy, allow researchers to determine the materials present on an asteroid's surface. Once suitable candidates are identified, space missions can be designed and launched to gather more detailed information. The extraction process could involve robotic spacecraft equipped with advanced mining technologies. These robots would be designed to land on or rendezvous with asteroids, using techniques such as drilling, scoop systems, or even cutting tools to collect material. Water, for instance, could be extracted to support life support systems for future crewed missions, or converted into fuel for spacecraft. Valuable metals can be processed on-site or returned to Earth for industrial use. Challenges exist in asteroid mining, including the need to develop technologies for operating in low-gravity and microgravity environments where conventional mining methods may not apply. Navigating the complex dynamics of space travel, as well as ensuring the safety of both the mining operations and the space environment, are significant considerations. Furthermore, legal and ethical frameworks will need to be established to manage the ownership and exploitation of space resources. As technology advances and our understanding of asteroids improves, mining these celestial bodies could become a reality in the coming decades. This endeavor holds the promise of not only providing critical resources for Earth's industries, but also facilitating future space exploration by enabling in-situ resource utilization, allowing spacecraft to refuel and repair in space rather than relying solely on supplies launched from Earth. The concept of a space elevator envisions a revolutionary transportation system that would dramatically change the way humans access space. Essentially, it consists of a cable or tether anchored to the surface of the Earth and extending into geostationary orbit, about 36,000 kilometers above the equator. The idea is that a counterweight positioned beyond geostationary orbit would maintain tension in the cable, allowing vehicles to climb up the tether to reach space, using energy-efficient mechanisms rather than traditional rocket propulsion. One of the most appealing aspects of a space elevator is its potential to reduce the cost of launching payloads into orbit. Currently, launching spacecraft requires enormous amounts of rocket fuel, resulting in high costs and significant environmental impacts. By utilizing a space elevator, payloads could be lifted gradually along the tether, requiring less energy compared to a traditional launch. This could make space more accessible for various applications, including satellite deployment, space tourism, and even planetary exploration. Additionally, a space elevator could facilitate a continuous flow of materials and people to and from orbit. This infrastructure would enable the construction of space stations or manufacturing facilities in orbit, potentially leading to the development of new technologies and industries that are currently impractical due to the logistical challenges associated with launches. Regular access to space would also support ongoing research efforts and international collaborations in areas such as astronomy, planetary science, and advanced technologies. However, building a space elevator presents significant engineering challenges. The material used for the tether would need to possess extraordinary strength-to-weight ratios, far exceeding that of any current technology. Carbon nanotubes and other advanced materials are being researched as potential candidates, but they have yet to be developed to the necessary scale and properties. Additionally, factors such as weather conditions, orbital debris, and the potential for space weather effects pose further risks that would need to be addressed. Despite these challenges, the vision of a space elevator highlights the potential for innovative solutions to revolutionize space travel. As research continues and technology advances, we may one day see such concepts transform the future of exploration and commercialization in space, making it a more routine endeavor for humanity. Spacecraft employ gravity assists or gravitational slingshots as a clever technique to gain speed and alter their trajectories while conserving fuel. This maneuver takes advantage of the gravitational pull of a planet or moon to increase the speed of the spacecraft without the need for additional propulsion. The basic principle is rooted in the conservation of momentum. As a spacecraft flies closely past a massive body, it essentially steals a small amount of the body's motion, resulting in an increase in velocity relative to the Sun. When a spacecraft approaches a planet, it follows a path that leans into the planet's gravity well. As it swings around the planet, it gains speed as it is pulled in and then flung out the other side. The spacecraft's trajectory can be adjusted intentionally during this flyby to optimize the resulting path. For instance, a spacecraft heading towards the outer solar system might use a close approach to a gas giant like Jupiter to gain extra velocity while being redirected toward its next destination. Tatami. The technique has been utilized in many notable missions. For example, the Voyager spacecraft famously slingshotted around multiple planets to extend their reach throughout the solar system. Voyager 1 and 2 made gravity assists at Jupiter and Saturn, enabling them to continue their journey to the outer planets while collecting invaluable data on those gas giants and their moons. Gravity assists not only facilitate faster travel, but also reduce the amount of propellant required on long missions, making them financially and practically feasible. This is particularly important for missions that aim to explore distant targets, as every bit of fuel saved can allow for longer missions and more extensive scientific endeavors. As astronauts and robots probe deeper into the solar system, understanding and effectively using gravitational assists remain essential strategies for successful exploration. Plans for establishing a permanent human presence on the Moon are gaining momentum as various space agencies and private companies push for lunar exploration. The United States, through NASA's Artemis program, aims to return astronauts to the lunar surface by the mid-2020s. This initiative sets the groundwork for sustainable exploration, focusing on the lunar South Pole, where water ice has been detected. Such resources could be essential for future human habitation and provide valuable insights into the Moon's geology and history. To facilitate this long-term presence, NASA intends to build the Lunar Gateway, a space station that will orbit the Moon. This gateway will serve as a staging point for missions to the surface and can support a range of activities, from scientific research to lunar operations. By collaborating with international partners and commercial entities, the gateway will enhance the capabilities necessary for exploratory missions, potentially leading to a more robust lunar economy. In parallel, the Artemis Base Camp is being proposed to support Artemis missions. This base would feature habitats, a lunar lander, and equipment for exploring the moon's surface. It is designed to allow astronauts to live and work on the moon for extended periods, searching for resources, conducting experiments, and preparing for future deep space missions to Mars and beyond. Other countries, such as China and Russia, are also developing their moon exploration programs. These initiatives may lead to a collaborative international approach, akin to what was seen with the International Space Station. As various nations and private companies converge on this goal, the moon is set to become a bustling hub for science and technology, paving the way for humanity's future in deeper space exploration. A planet's potential habitability primarily hinges on several key factors that create conditions suitable for life as we understand it. Foremost among these is the presence of liquid water, often referred to as the universal solvent. Water is essential for biochemical processes, and a planet needs to be in the habitable zone around its star, where temperatures allow water to remain in a liquid state. This region varies depending on the star's characteristics, but it typically lies at a distance where conditions are just right, not too hot, making water vaporize, and not too cold, causing it to freeze. Another critical factor is the planet's atmosphere. A stable atmosphere can provide the necessary pressure to support liquid water and protect potential life forms from harmful cosmic radiation and extreme temperatures. The composition of the atmosphere is also important. It must contain essential gases like oxygen or carbon dioxide, which are vital for various forms of life, and should maintain the right balance to sustain a climate conducive to life. Geological activity, or tectonic processes, also plays a crucial role in a planet's habitability. Such activity can recycle nutrients and gases, maintaining an environment that supports life over geological timescales. Additionally, a planet's magnetic field can shield its atmosphere from solar winds, preserving it against erosion and helping to sustain long-term conditions that are favorable for life. Finally, the presence of organic molecules, carbon-based compounds that are the building blocks of life, can indicate a planet's potential. Such molecules may form through various natural processes and are vital for life as we know it. Collectively, these factors create a framework for identifying planets that may harbor life, or at least possess the necessary conditions for life to emerge. As of now, scientists have discovered thousands of exoplanets, and among them, a significant number are considered potentially habitable. According to current estimates, there are over 4,000 confirmed exoplanets, with more than 100 classified as potentially habitable. These potentially habitable exoplanets are located in the habitable zones of their stars, where temperatures allow for liquid water to exist if the right atmospheric conditions are present. The search for exoplanets has primarily been conducted by missions such as NASA's Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, or TESS. These missions have dramatically expanded our understanding of planetary systems beyond our own, identifying planets of various sizes and compositions. The criteria for classifying a planet as potentially habitable include its size, distance from its star, and the presence of the right atmospheric conditions, suggesting that it could support life. Additional studies are ongoing to further refine our understanding of these intriguing worlds. Scientists are now using ground-based telescopes and advanced techniques to gather more data about the atmospheres of these exoplanets. This information is vital for assessing their habitability more accurately and determining whether they contain the necessary elements and conditions to support life. As technology continues to advance and more sophisticated missions are planned, the number of identified potentially habitable exoplanets is expected to grow. The search for life beyond Earth remains one of the most fascinating endeavors in modern astronomy, opening a window to the vast possibilities of life in the universe. The Goldilocks zone, often referred to as the habitable zone, is a region around a star where conditions are just right for liquid water to exist on a planet's surface. This concept borrows its name from the popular fairy tale of Goldilocks, where the protagonist finds the porridge that is not too hot, not too cold, but just the right temperature. In astrobiology, this zone is crucial because liquid water is considered essential for life as we know it, serving as a solvent for biochemical reactions and a medium in which life can thrive. The boundaries of the Goldilocks zone vary depending on the type and size of the star. For instance, a smaller, cooler star will have a closer habitable zone compared to a larger hot star, where the habitable zone may be much further away. Earth lies comfortably within the habitable zone of the Sun, allowing for stable temperatures that support the existence of liquid water and, consequently, diverse life forms. Identifying exoplanets within these zones is a primary focus for scientists searching for signs of life beyond our solar system. The importance of the Goldilocks zone in the search for extraterrestrial life cannot be overstated. When astronomers discover a planet within this zone, it raises the likelihood that conditions could be suitable for life, warranting further investigation. However, it is essential to note that simply being in the Goldilocks zone does not guarantee that a planet is habitable. Factors such as atmospheric composition, geological activity, and potential magnetic fields also play significant roles in determining a planet's ability to support life. Moreover, the concept of the Goldilocks zone is expanding as we learn more about the adaptability of life. Some extremophiles on Earth thrive in conditions previously thought to be unlivable, prompting scientists to consider the possibility of life existing outside the traditional habitable zones. This evolving perspective enriches our understanding of where life might exist in the cosmos, making the quest for habitable worlds even more compelling. Scientists employ a variety of methods to search for signs of life on exoplanets, focusing primarily on atmospheric analysis and direct imaging. One of the most common techniques is spectroscopy. When a planet transits in front of its host star, some of the star's light filters through the planet's atmosphere. By studying the resulting spectrum of light, scientists can identify the presence of specific gases, such as oxygen, methane, or carbon dioxide. These gases, particularly when found in combination, may indicate biological processes, as they are often associated with living organisms on Earth. Another approach involves looking for markers of habitability through astrobiological models. Scientists use data from missions like NASA's Kepler and TESS to identify potentially habitable exoplanets within the Goldilocks zone. Once these candidates are selected, simulations can be performed to predict atmospheric conditions and how they would behave under various scenarios, enhancing the understanding of these worlds and their potential for hosting life. Direct imaging is another method used to observe exoplanets. While challenging due to the brightness of stars, advancements in telescope technology, such as the upcoming James Webb Space Telescope, are expected to facilitate the capture of images of exoplanets. This method may provide clues about surface conditions and features, further informing scientists whether these planets could support life or display signs of biological activity. Furthermore, the study of planet-hosting stars contributes to this search. Stellar properties such as mass, stability, and the presence of stellar flares can affect the habitability of planets in their systems. By neutron analyzing star characteristics alongside planetary data, scientists can better assess which exoplanets may hold the greatest potential for life. As technology continues to improve and new missions are launched, our ability to detect signs of life on distant worlds is likely to advance significantly, expanding our understanding of the cosmos. The exploration of exoplanets has unveiled a fascinating variety of worlds, some of which defy our expectations and challenge our understanding of planetary systems. One such example is WASP-17b, an exoplanet known as a hot Jupiter. This gas giant orbits incredibly close to its host star, leading to scorching surface temperatures that reach over 1,000 degrees Celsius. The extreme conditions on WASP-17b create a unique environment where atmospheric phenomena, such as rapidly moving winds and likely rain made of molten glass, occur. Another curious find is HD 209458b, often called Osiris. This exoplanet is notable for its dramatic atmospheric loss. It exhibits a trailing tail of gases stripped away by the intense radiation from its star. Observations have shown that the atmosphere of Osiris is being eroded at a rapid pace, offering insights into the processes that can affect a planet's atmosphere and potential habitability over time. Then there is Kepler 2014b, a super-Earth that presents an enigmatic, weighty mystery. This planet is almost twice the size of our Earth, but it is incredibly dense. Its density suggests that it might be composed largely of rock or some other material not commonly found in our solar system. Understanding the composition of such exoplanets can provide clues about planetary formation and the conditions prevalent in their systems. Lastly, the strikingly unusual planet LHS 806, also known as the Pancake. This planet features a remarkably elongated shape due to its rapid rotation, making it appear flattened at the poles. This distortion raises intriguing questions about how a planet's rotation can influence its structure and presents an opportunity for researchers to learn about the diverse characteristics that exoplanets can exhibit. The study of these strange exoplanets expands our comprehension of what is possible in the cosmos and sparks curiosity about life beyond our own solar system. Astronomers employ a variety of sophisticated techniques to study the atmospheres of exoplanets, providing vital insights into their composition and potential habitability. One of the most effective methods is transmission spectroscopy. This technique involves observing a planet as it transits in front of its host star. When the planet passes in front, some of the star's light filters through its atmosphere. By analyzing the spectrum of this light, scientists can identify the specific wavelengths absorbed by various gases, allowing them to infer the atmospheric composition. Another method used is secondary eclipse spectroscopy. This occurs when an exoplanet moves behind its star, allowing astronomers to compare the light from the star alone to that of the star and planet together. By examining the differences in the light spectrum during these two phases, scientists can determine how much light is being emitted or reflected by the planet and use that information to extract data about its atmosphere. Direct imaging also plays a role in studying exoplanet atmospheres. While challenging due to the brightness of host stars, advanced imaging techniques such as coronography and star shades allow astronomers to block out the star's light and capture images of the planets themselves. This gives researchers the chance to gather direct data about the atmospheric properties of certain exoplanets. In addition to these observational techniques, computer models are crucial for interpreting data gathered from these methods. Scientists use simulations to understand how various atmospheric gases interact with light and to model how different compositions might respond to solar radiation and other environmental factors. By combining observational data with robust theoretical frameworks, astronomers can paint a clearer picture of exoplanet atmospheres, enhancing our understanding of these distant worlds and their potential for supporting life. Panspermia is a fascinating hypothesis suggesting that life on Earth, and potentially elsewhere in the universe, may have originated from microbial life or organic compounds that traveled through space. This theory posits that life could spread between celestial bodies via comets, meteoroids, and cosmic dust. It raises the intriguing possibility that life's building blocks exist beyond our planet, hinting at the interconnectedness of life throughout the cosmos. There are several variations of the panspermia hypothesis. One such version proposes that microscopic life forms, such as bacteria, could survive the harsh conditions of space travel. These organisms might remain dormant during transportation and then become active upon reaching a suitable environment, like a planet with the right conditions for growth, like Earth. The endurance of extremophiles on our planet, which can withstand extreme temperatures, radiation, and vacuum, supports the notion that life could survive the journey through space. Another aspect of panspermia involves the delivery of organic compounds rather than fully formed life. Research suggests that complex organic molecules such as amino acids and nucleotide precursors might be formed in interstellar space and delivered to planets through meteoritic impacts. This theory aligns with the origin of life experiments conducted on Earth, which demonstrate that simple organic molecules can form under prebiotic conditions. If these compounds were delivered to Earth, they might have played a significant role in the emergence of life. Panspermia also raises profound questions about the prevalence of life in the universe. If life's building blocks are widespread throughout the cosmos, it increases the likelihood that life could exist elsewhere. It encourages a broader view of life's origins, suggesting that the universe might be teeming with potential for life, shaped by the movement of materials across vast distances and different celestial environments. This interconnectedness emphasizes the mysteries of life, both on Earth and beyond, inviting further exploration into the cosmos. Rogue planets are fascinating celestial objects that drift through space unattached to any star. Their formation can occur through several mechanisms. One prevalent theory suggests that rogue planets originate in planetary systems where they experience gravitational interactions or perturbations that disturb their orbits. These interactions can be caused by larger planets or even the gravitational pull of nearby stars. Such events might result in a planet being ejected from its original system, sending it into the vast expanse between stars. Another possibility involves the formation of rogue planets in isolation. Some planets may form in the protoplanetary disk of a young star system, but instead of being captured by a star's gravitational pull, they can form in regions with insufficient mass to develop a stable orbit within the system. These planets can then find themselves unbound and become rogue as they continue to drift through space. As for their prevalence, studies suggest that rogue planets might be surprisingly common in our galaxy. Estimates from various research endeavors indicate that there could be several billion rogue planets roaming freely through the Milky Way alone. These estimates stem from observations using advanced telescopes and models of planetary formation, which reveal that star systems can have multiple planets, increasing the likelihood that some will ultimately be ejected. The existence of rogue planets presents compelling questions about the nature of planetary systems and the conditions that lead to their formation. The search for these solitary worlds is ongoing, with astronomers using various techniques to detect them. Observing rogue planets not only offers insights into their properties, but also prompts deeper inquiries into how they may interact with other celestial bodies in their journeys through the cosmos, including their potential to harbor life in the absence of a host star. Super-Earths are a category of exoplanets that have a mass greater than Earth's, but significantly less than that of our solar system's gas giants, like Neptune and Uranus. Typically, super-Earths range in mass from 1 to 10 times that of Earth and can vary widely in composition and atmosphere. They may be rocky like our planet, or they could possess thick gaseous envelopes depending on their characteristics and formation histories. This diversity makes super-Earths fascinating subjects of study for astronomers and astrobiologists alike. The interest in super-Earths is driven by their potential to host conditions suitable for life. Many of these planets exist within the habitable zones of their stars, where temperatures allow for liquid water to exist, a crucial ingredient for life as we understand it. Additionally, the variety of sizes and compositions among super-Earths raises questions about their geological activity, atmospheric retention, and potential habitability. Understanding these factors can help scientists learn more about the diversity and resilience of life in different environments. Furthermore, the discovery of super-Earths challenges our understanding of planetary formation and the characteristics of planetary systems. Their widespread presence suggests that the formation of planets can take many forms and occur under various conditions. As astronomers use advanced telescopes to study super-Earth atmospheres and surface conditions, they hope to glean insights into how these planets evolve and how life might emerge and adapt in diverse environments. As the search for extraterrestrial life continues, super-Earths provide a promising frontier. Their proximity and favorable conditions place them among the most intriguing candidates for future explorations, whether through direct observation or by analyzing their atmospheres for biosignatures. The ongoing study of super-Earths is reshaping our understanding of the universe and expanding the possibilities of where life might exist beyond our solar system. Life evolving on planets orbiting red dwarf stars presents unique challenges and intriguing possibilities. Red dwarf stars, also known as M-dwarfs, are the most common type of stars in the universe. They are significantly smaller and cooler than our Sun, with much longer lifetimes, often lasting for tens to hundreds of billions of years. This extended lifespan provides stable environments for planets in their habitable zones, which tend to be much closer to the star compared to planets in the habitable zones of larger stars. One major consideration is the habitability of planets around red dwarfs, particularly their exposure to stellar flares. Red dwarfs are known for their stellar activity, often emitting powerful flares that can inundate nearby planets with radiation. This could have profound effects on the atmospheres of such planets, potentially stripping them of protective layers. If a planet can maintain a stable atmosphere in spite of this activity, it could create environments conducive to life. Any life forms developing here would need to adapt to these conditions, possibly evolving protective mechanisms against radiation or developing in subsurface habitats. The proximity of the habitable zone to red dwarf stars also means that planets may become tidally locked, where one side always faces the star while the other remains in perpetual darkness. This situation could lead to significant temperature differences across the planet, creating unique climate patterns. Life on such worlds might evolve distinct adaptations to survive extreme conditions, perhaps thriving in twilight zones where temperatures are more moderate and sunlight is accessible. Additionally, the long time frames of red dwarf stars allow ample opportunity for life to evolve and adapt. With billions of years available for evolutionary processes, ecosystems might develop in unexpected ways, potentially leading to resilience against environmental extremes. While the specific pathways for life around red dwarfs remain speculative, studying these systems is vital in our quest to understand potential life forms in various stellar environments. Scientists are increasingly focusing on red dwarf systems, as their prevalence in the galaxy raises the exciting possibility that they could harbor life forms unlike anything we know. The observable universe is vast, encompassing an estimated diameter of around 92 billion light-years. This immense distance reflects the limits of what we can see based on the age of the universe and the finite speed of light. The universe has been expanding since the Big Bang, which occurred approximately 13.8 billion years ago. As a result, light from the most distant objects has taken billions of years to reach us, giving us a glimpse into the very early history of the cosmos. Scientists have reached this conclusion through a combination of astronomical observations and theoretical models. One of the key methods is the study of cosmic microwave background radiation, which is the afterglow of the Big Bang. By analyzing its uniformity and slight variations, astronomers gain insights into the metrics of the universe's expansion and its large-scale structure. The instruments used for this purpose, such as the Wilkinson Microwave Anisotropy Probe and the Planck satellite, provide crucial data for understanding the universe's age and size. Another important component in measuring the observable universe involves observing distant galaxies and their redshifts. As the universe expands, galaxies move away from us. This movement shifts the light they emit to longer wavelengths, a phenomenon known as redshift. By examining how much the light from these galaxies is redshifted, scientists can calculate their distance and speed, providing information about the rate at which the universe is expanding, known as the Hubble constant. While the observable universe is extensive, it is essential to recognize that it is only a part of the total universe. Beyond what we can see, the universe may extend infinitely or contain regions beyond our observational capabilities. The methods used to quantify the observable universe combine observational astronomy with theoretical frameworks, allowing us to construct a detailed picture of our cosmic surroundings, even as we continue to explore the mysteries that lie beyond our reach. A light year is a unit of distance that represents the distance light travels in 1 year in a vacuum. Since light moves at an astonishing speed of approximately 300,000 kilometers per second, a light year equates to about 9 trillion kilometers in distance. This vast measure allows astronomers to convey the immense scales of the universe in more comprehensible terms. In astronomical contexts, a light year is used to express distances between celestial bodies and other cosmic objects, making it a practical unit for understanding the vastness of space. For example, when we say that Proxima Centauri, the closest star to our solar system, is about 4 light years away, it means that light from that star takes 4 years to reach us. This distance measurement provides a clearer perspective on how far away objects are compared to familiar terrestrial distances that can often seem inadequate for cosmic scales. Astronomers use light years to chart distances across the universe, from nearby stars to distant galaxies. This unit helps in delineating the size of our Milky Way galaxy, which is about 100,000 light-years across, and even in describing the scale of the observable universe, which can extend billions of light-years in all directions. By employing light-years, scientists can effectively communicate and quantify the astonishing distances involved in cosmic exploration. Additionally, understanding light years helps astronomers study the light that reaches us from these distant objects. Since the universe is constantly expanding, the light emitted by galaxies also provides important information about their motion and the history of the universe. By measuring cosmic distances in light years, scientists glean valuable insights into the dynamics and evolution of the cosmos, bridging the gap between our observable world and the expansive universe beyond. Astronomers utilize the cosmic distance ladder, a systematic method for measuring distances in the universe to navigate the vast expanses of space. This approach employs a series of interconnected techniques, each geared toward measuring distances to increasingly distant objects. The concept is akin to a ladder, where each rung represents a different method that builds upon the previous ones, allowing astronomers to ascend to greater distances. The first rung of the ladder involves parallax, a technique used for measuring distances to nearby stars. By observing a star's position at different times of the year and noting its apparent shift against more distant background stars, astronomers can calculate its distance based on the angle of this apparent movement. This method is effective for stars within a few hundred light-years from Earth, providing a reliable baseline for distance measurements. As astronomers climb higher on the ladder, they turn to standard candles, particularly Cepheid variable stars. These stars exhibit a consistent relationship between their pulsation period and their intrinsic brightness. By measuring how bright a Cepheid appears from Earth, astronomers can compare this apparent brightness to its actual brightness. This allows them to calculate the distance to the star. This method extends the cosmic distance ladder to thousands of light-years. For even greater distances, astronomers rely on Type Ia supernovae, which serve as excellent standard candles due to their predictable peak brightness. When these supernovae occur in distant galaxies, astronomers can use their brightness to determine the distances to those galaxies. Combining this information with data on redshifts, how much the light from these galaxies shifts towards the red end of the spectrum due to the universe's expansion, helps astronomers measure distances across billions of light-years. As each rung of the cosmic distance ladder builds upon the previous one, astronomers can create a comprehensive picture of the universe's structure and scale. This hierarchical approach is crucial for mapping out the cosmos, allowing scientists to measure distances accurately and explore the fundamental characteristics of celestial objects, ultimately enhancing our understanding of the universe itself. The concept of cosmic horizons refers to the limits of our observable universe, beyond which we cannot receive information. These horizons are influenced by the expansion of the universe, which means that there are regions of space that are moving away from us faster than light can travel. Consequently, light from those regions will never reach us, effectively creating a boundary to our observable universe. The two key types of cosmic horizons are the particle horizon and the event horizon. The particle horizon represents the maximum distance from which light has had time to reach us since the beginning of the universe. This boundary defines the size of the observable universe and informs us about the extent of the regions we can see, which is composed of galaxies, cosmic background radiation, and other astronomical phenomena. The particle horizon continues to grow as the universe expands, allowing us to observe increasingly distant objects as time progresses. The event horizon, on the other hand, delineates the boundary of the observable universe from a future perspective. It indicates the limit beyond which events occurring will never be observable due to the acceleration of the universe's expansion. As time goes on, more regions will fall beyond this horizon, eventually leading to a diminishing observable universe. This concept poses intriguing implications for our understanding of the ultimate fate of the universe and the potential for observing its contents. Cosmic horizons are essential for understanding the fundamentals of cosmology, as they help astronomers and physicists decipher the history and evolution of the universe. They inform theories about the early universe's conditions, the formation of galaxies, and the nature of cosmic expansion. By studying cosmic horizons, scientists can explore concepts like dark energy and the dynamics of expansion, allowing for a deeper understanding of the structure and fate of the cosmos. The implications of cosmic horizons challenge our perceptions of space and time, emphasizing the limitations of human observation in the grand tapestry of the universe. The expansion of the universe profoundly alters our ability to observe distant objects. As the universe expands, galaxies are not just moving away from us, they are actually getting more distant over time. This phenomenon is dictated by the very fabric of space itself stretching, which means that light emitted from these galaxies is also stretched, leading to what scientists call redshift. As the light waves travel across expanding distances, they get longer, pushing them towards the red end of the spectrum. This redshift impacts how we view light from distant galaxies. An object located billions of light years away may have emitted its light long before the universe reached its current size. Consequently, when that light finally arrives at Earth, it has transformed, often moving from visible wavelengths into infrared or even microwave wavelengths. This shift can make it challenging to detect such objects using traditional optical telescopes, which are designed to observe light within the visible spectrum. Moreover, the increase in distance due to the universe's expansion also means that astronomical phenomena are becoming increasingly isolating. As galaxies soar away from each other, some might eventually cross beyond our observable horizon, effectively disappearing from view. Over time, the universe is projected to become darker and less populated as more and more galaxies retreat beyond the limits of observation. The intriguing aspect of this cosmic dance is that not only are we losing some sight of our universe, but it also challenges our understanding of cosmic structures. Our current technology, including powerful space-based telescopes like the Hubble Space Telescope, allows us to look further into the past than ever before, capturing moments from the universe's early stages. However, as the universe continues to expand, the future of observation could alter drastically, pushing the boundaries of what we perceive and understand. The largest known void in the universe is the Great Void, also referred to as the Giant Void or the Central Void. This immense region of space stretches approximately 100 million light-years across and lies at the heart of a cosmic structure known as the local supercluster. Such voids are vast expanses of relatively empty space that contain significantly fewer galaxies compared to denser regions, making them fascinating subjects of study in cosmology. These voids form as a result of gravitational interactions and the large-scale structure of the universe. Over billions of years, matter has clumped together under gravity, forming galaxies, clusters, and superclusters. The regions that do not accumulate matter create these enormous voids. The Great Void is not entirely empty. There are still some galaxies scattered within it, but their density is much lower than in surrounding areas. In the context of the universe's overall structure, the Great Void exemplifies one of the many features of cosmic topology. It showcases how the universe is a complex tapestry woven from denser regions surrounded by vast empty spaces. These voids influence the movement and distribution of galaxies, playing a crucial role in how matter is organized on a gigantic scale. Studying the Great Void deepens our insight into the universe's history and evolution. It challenges our understanding of cosmic formation and provides clues about the distribution of dark matter and dark energy. As researchers continue to explore these vast empty spaces, they uncover more about the intricacies of our universe and the forces shaping it over cosmic time. Astronomers determine the age of the universe through a combination of observational techniques and theoretical models, primarily relying on the concepts of cosmic expansion and the cosmic microwave background radiation. One of the fundamental tools for measuring the age of the universe is the Hubble constant, which quantifies the rate at which galaxies are moving away from us due to the expansion of space. By measuring the redshift of light from distant galaxies, astronomers can calculate how long it has taken for those galaxies to reach their current positions, providing a time frame for the universe's expansion. Another crucial element in this measurement is the analysis of the cosmic microwave background radiation, which is the afterglow of the Big Bang. Detected nearly uniformly across the sky, this radiation contains vital information about the early universe. The temperature fluctuations in this radiation reflect the density variations present during its formation. By studying these fluctuations, scientists can infer the density and composition of the universe, leading to accurate models describing how the universe evolved over time. This data helps refine estimates of its age. Additionally, astronomers study the oldest known stars to pinpoint the universe's age. By examining stars known as population 2 stars, which reside in globular clusters, they can establish an age limit. These ancient stars formed shortly after the Big Bang, so the age of the oldest stars offers a minimum age for the universe itself. Current estimates suggest that the universe is approximately 13.8 billion years old, derived from the combination of these various measurements and models. The collaboration between observational data and theoretical physics allows for a comprehensive understanding of the universe's timeline. As technology improves and our observational capacity grows, astronomers continue to refine their models and measurements, enhancing our grasp of not just the universe's age, but also its complex evolution through time. Cosmic inflation is a theory that describes the extremely rapid expansion of the universe that occurred just after the Big Bang. According to this concept, in the first fraction of a second, specifically around 10 to the power of negative 30 seconds, to about 10 to the power of negative 20 seconds after the Big Bang, the universe expanded exponentially. This expansion was so swift that it caused the universe to grow from subatomic scales to about the size of a grapefruit, fundamentally altering its size in a short span. The inflationary model helps address several perplexing questions about the universe, such as its large-scale uniformity, flatness, and the distribution of cosmic structures we observe today. Before inflation was proposed, scientists struggled to explain why distant regions of the universe appeared so remarkably similar in temperature and density, despite being too far apart to have interacted. Inflation suggests that these regions were once in close proximity before being pushed apart by this rapid expansion. This phenomenon provides a compelling answer to the uniformity observed in the cosmic microwave background radiation. Moreover, cosmic inflation serves as a framework for understanding the large-scale structure of the universe. During inflation, quantum fluctuations in the fabric of spacetime were stretched to macroscopic scales, seeding the density variations that would eventually evolve into galaxies, stars, and clusters. Without this process, the universe as we know it would lack the intricate distribution of matter that has formed over billions of years. The implications of inflation extend beyond merely explaining the universe's size. It shapes our comprehension of the cosmos and suggests that our universe might be just one of many within a grander multiverse. This bold idea continues to inspire astronomers and physicists as they seek to unravel the mysteries of our universe's origins and evolution. Astronomers use the method of parallax to measure distances to nearby stars by observing the apparent motion of the stars against distant background objects, such as more distant stars or galaxies, as the Earth orbits around the Sun. The principle behind parallax involves basic geometry. As the viewpoint changes, nearby objects appear to shift relative to more distant ones. This method is particularly effective because it allows astronomers to calculate how far away a star is based on the angle of this apparent shift. To apply parallax, observers take two measurements of a star's position at different points in Earth's orbit, usually 6 months apart. During this period, the Earth moves to the opposite side of its orbit around the Sun, creating two vantage points separated by the diameter of Earth's orbit. The angle formed between these two positions and the star is known as the parallax angle. A smaller angle indicates that a star is further away, while a larger angle indicates proximity. Using this parallax angle, astronomers apply a formula derived from trigonometry. By knowing the baseline distance between the two measurement points, essentially the radius of Earth's orbit, and the measured angle, they can calculate the distance to the star in parsecs. 1 parsec is defined as the distance at which one astronomical unit subtends an angle of 1 arc-second, which directly relates to the observed parallax angle. While this method works remarkably well for stars up to about 300 light-years away, it becomes challenging for more distant stars because the angle of parallax becomes increasingly small and difficult to measure accurately. Advances in technology, such as space-based telescopes like the Gaia spacecraft, enhance the precision of these measurements, allowing for more accurate distance estimates of stars and contributing to our understanding of the Milky Way and beyond. Parallax remains one of the fundamental techniques in astrometry, highlighting how geometry can unravel the mysteries of our universe. The local group is a collection of galaxies that includes our own Milky Way, the Andromeda Galaxy, and about 50 other smaller galaxies. This gravitationally bound grouping spans roughly 10 million light-years across and is part of a larger cosmic structure, the Virgo supercluster. Within the local group, the Milky Way and Andromeda are the two largest galaxies, and they each have numerous smaller companions, such as the Magellanic Clouds, that orbit them. In the grander scheme of the universe, the local group is a small but significant component of the large-scale structures formed by the distribution of matter across the cosmos. Galaxies congregate into clusters, and these clusters can form superclusters, creating a broad network of filaments and voids that define the universe's architecture. The Virgo supercluster is one of the major regions where such groups coexist, showcasing many clusters of galaxies that are in proximity to one another. The gravitational interactions within the local group affect the dynamics of its member galaxies, influencing their movements and eventual fates. For instance, the Milky Way and Andromeda are on a collision course and will merge in about 4 billion years. Such interactions are crucial for understanding galaxy evolution, star formation, and the role of dark matter in shaping galaxy clusters. As astronomers study the local group, they gain insights into the processes that govern galaxy formation and clustering on larger scales. Observations of our immediate cosmic neighborhood help astronomers piece together a broader picture of the universe's history and its continuing evolution, revealing how smaller groups like the local group fit into the intricate tapestry of the cosmos. The conditions near the surface of a neutron star are extraordinarily extreme, making them some of the most hostile environments in the universe. Neutron stars form from the remnants of massive stars that have undergone supernova explosions, collapsing under their own gravity. This collapse leads to an incredibly dense core primarily composed of neutrons, along with significant amounts of other particles. A typical neutron star has a mass greater than that of the Sun, but is compressed into a sphere with a radius of only about 10 kilometers. The surface gravity of a neutron star is about 2 billion times stronger than that of Earth. This immense gravitational pull significantly affects time and space around the star, as predicted by Einstein's theory of general relativity. Due to this intense gravity, the escape velocity at the surface exceeds the speed of light, creating conditions where standard physics breaks down and leads to fascinating phenomena such as gravitational time dilation. Temperature near the surface of a neutron star can reach incredibly high levels, often exceeding 1 million degrees Celsius immediately following its formation. As the star ages, this temperature decreases over time, but even cooler neutron stars can still radiate significant amounts of X-rays as they cool. The surface itself is thought to be composed of a solid crust of molten iron, along with a superfluid ocean of neutrons and a core that may contain exotic states of matter. Furthermore, neutron stars often produce strong magnetic fields, sometimes 1 trillion times stronger than Earth's magnetic field. These magnetic fields can accelerate charged particles and generate beams of radiation that we observe as pulsars when they sweep across our line of sight. The combination of extreme density, gravity, temperature, and magnetic fields makes neutron stars a fascinating subject of study for astronomers, revealing insights into fundamental physics under conditions not replicable on Earth. The core of the Sun reaches staggering temperatures around 15 million degrees Celsius. This incredible heat is generated through the process of nuclear fusion, where hydrogen nuclei collide and fuse to form helium, releasing vast amounts of energy in the form of light and heat. This fusion process powers the Sun and is essential for producing the energy that sustains life on Earth. Measuring the temperature of the Sun's core directly is impossible due to its dense and opaque layers, but scientists use indirect methods to infer this temperature. One primary technique involves studying solar oscillations or vibrations known as helioseismology. These oscillations are akin to sound waves traveling through the Sun, and by analyzing their patterns and frequencies, scientists can gain insights into the Sun's internal structure. Different layers of the Sun, including the core, reflect these oscillations differently, allowing researchers to model temperature and pressure in various regions. In addition to helioseismology, scientists apply the laws of physics to theoretical models of stellar evolution. These models simulate how stars like our Sun evolve over time, factoring in variables such as mass, luminosity, and chemical composition. By refining these models with observational data, researchers can make informed estimates about core temperatures and other properties. Finally, experiments on Earth, like those conducted at fusion laboratories, allow scientists to recreate the conditions found in the Sun's core. By studying how hydrogen behaves under high temperature and pressure, they can validate their models and assumptions regarding the fusion processes that occur within the Sun. This combination of indirect measurement techniques and theoretical modeling ultimately helps us understand the extreme conditions at the core of our closest star. Extreme weather phenomena on other planets showcase the incredible diversity and variety of environmental conditions beyond Earth. The most notorious examples can be found within our own solar system. For instance, Jupiter's Great Red Spot is a massive storm, larger than Earth itself, that has been raging for hundreds of years. This swirling hurricane features wind speeds exceeding 400 kilometers per hour and presents a striking reddish color due to its complex atmospheric chemistry. On Saturn, another astonishing weather phenomenon is the hexagonal storm at its north pole. This uniquely structured storm has a shape reminiscent of a hexagon and spans approximately 25,000 kilometers across. The winds around this hexagon can reach speeds of about 225 kilometers per hour. Saturn experiences seasonal changes, which can alter the storm's dynamics and shape, contributing to the planet's rich meteorological tapestry. Mars, with its thin atmosphere, experiences some of the most intense dust storms in the solar system, capable of enveloping the entire planet. These storms can last for weeks and significantly reduce visibility, impacting surface temperatures. The most massive dust storms can even create a global temperature rise by tens of degrees Celsius, making Martian weather quite extreme despite its cold climate. Venus presents yet another fascinating realm of extreme weather. Its thick atmosphere is mostly carbon dioxide, with clouds of sulfuric acid, leading to incredibly high surface temperatures around 460 degrees Celsius. The atmospheric pressure on Venus is about 92 times that of Earth, creating an environment reminiscent of the crushing depths of Earth's oceans. The combination of high temperatures, corrosive clouds, and heavy pressure generates a unique type of weather system, often characterized by superrotational winds that move much faster than the planet's rotation itself. The diversity of weather phenomena throughout our solar system offers a glimpse into the complex atmospheres and extreme conditions that exist beyond our own planet, with each world revealing its unique secrets through the study of its atmospheric dynamics. In the depths of space, temperatures can plummet to astonishingly low levels. The average temperature of the cosmos is around 2.7 degrees above absolute zero, translating to temperature values of about -270 degrees Celsius. However, in some areas, especially in the presence of vast expanses devoid of matter and heat, temperatures can approach absolute zero, a theoretical point where the motion of molecules would come to a complete halt. The coldest known place in the universe was found in a region of the Boomerang Nebula, where temperatures dip down to about -272 degrees Celsius. This nebula is located roughly 5,000 light-years away from Earth. The extreme cold in the Boomerang Nebula is primarily due to the rapid expansion of gas expelled from the dying star at its center, which cools as it expands. This unique combination of conditions has enabled the nebula to achieve such frigid temperatures. On Earth, scientists have been able to reach lasting low temperatures in controlled laboratory settings, such as in experiments involving laser cooling techniques. In these environments, temperatures have been brought as close as 1/1000th of a degree above absolute zero. Such extreme cold allows researchers to explore quantum mechanical effects and gain deeper insights into the behavior of matter under unusual conditions. Studying these frigid areas helps astronomers understand the processes that occur in space and the characteristics of cosmic bodies. The knowledge gathered from these investigations contributes to our broader understanding of the universe and the fundamental principles of physics. The cold expanses of space remind us of the extraordinary extremes that exist beyond our own warm, comfortable world. Standing on the surface of Venus would be an astonishing experience, but incredibly hostile and completely uninhabitable for humans. Venus is often referred to as Earth's twin due to its similar size and proximity, yet the conditions there are vastly different. The atmosphere of Venus is composed mainly of carbon dioxide, with clouds of sulfuric acid, creating an oppressive environment that traps heat through a runaway greenhouse effect. As a result, the surface temperature hovers around 460 degrees Celsius, hotter than the surface of Mercury, even though Venus is farther from the Sun. The atmospheric pressure at the surface of Venus is about 92 times that of Earth, equivalent to the pressure found nearly 1 kilometer deep in Earth's oceans. This extreme pressure would crush any human or spacecraft not specifically engineered to withstand it. The thick clouds shroud the surface from direct sunlight, creating a perpetually overcast sky with visibility limited to just a few meters due to the dense atmosphere. The clouds, composed of sulfuric acid droplets, rain down but evaporate before they can reach the surface due to the intense heat. Despite the extreme conditions, the landscape on Venus is remarkably varied, featuring mountains, volcanic plains, and large volcanic structures. Some scientists speculate that it has active volcanoes, and recent studies hint at potential volcanic activity. The rocky terrain would be barren, with no signs of water or life as we know it. Temperatures and pressures aside, the chemical composition of the atmosphere would be lethal, with corrosive clouds and an abundance of extreme gases posing serious challenges for any exploratory missions. Overall, standing on Venus would be a surreal experience bathed in a hellish environment, a stark reminder of how different planetary conditions can be within our own solar system. Although the planet remains a subject of significant scientific interest, it presents profound challenges for exploration and remains inhospitable to life as we understand it. Stars in the crowded centers of globular clusters manage to thrive despite the high density of stars and gravitational interactions around them through several fascinating mechanisms. Globular clusters are densely packed collections of stars, often containing hundreds of thousands to millions of them within a relatively small area of space. This concentration leads to increased gravitational interactions, which can drive various stellar dynamics and behaviors. One important aspect of star survival in these environments is their ability to maintain stability despite close encounters with other stars. While gravitational interactions can lead to exchanges of momentum, causing some stars to be ejected from the cluster or to merge, many stars find a balance that allows them to remain safely in orbit around the cluster's center. The gravitational potential well of the cluster acts to hold stars in place, helping to keep them from spiraling into the center or being flung out entirely. Another fascinating factor is the process known as dynamical relaxation. Over time, stars in a globular cluster interact with one another, redistributing their velocities and energies through numerous close encounters. This process creates a more stable configuration, allowing stars to settle into more predictable orbits. While these interactions can occasionally lead to violent outcomes, such as the formation of binary star systems or even supernovae, many stars adjust to their surroundings and persist within their stellar communities. Additionally, many globular clusters are ancient, and the stars within them often possess lower metallicities compared to stars in other regions of the universe. This low metallicity influences the lifetimes of these stars, often leading to longer lifespans. Many of the stars in these clusters are older red giants or yellow giants, which can survive for billions of years without the influences of environmental factors that typically affect younger, more volatile stars. Ultimately, the survival of stars in the crowded centers of globular clusters reveals a delicate interplay between gravitational forces, stellar interactions, and unique stellar evolution processes. These factors allow stars to continuously thrive in a dynamic, resource-rich environment that is both vibrant and competitive. Interstellar space, the vast expanse between star systems within a galaxy, presents a remarkably different environment compared to what we experience on Earth. This region is characterized by an average vacuum, with extremely low densities of matter, approximately 1 atom per cubic centimeter. The near absence of gas and dust means that interstellar space is largely empty, creating conditions that are far removed from the conditions found within stars or planetary atmospheres. Despite the scarcity of matter, interstellar space is not completely devoid of elements. The gas present is primarily composed of hydrogen and helium, along with trace amounts of heavier elements. Regions of higher density, known as molecular clouds, can form in interstellar space, hosting the raw materials for new star formation. These clouds can contain molecules and dust that provide crucial building blocks for stars and planets. Temperatures in interstellar space vary significantly, but are generally extremely cold, often reaching around 2.7 degrees Kelvin, which is the temperature of the cosmic microwave background radiation. However, within denser molecular clouds, temperatures can be higher, sometimes reaching several tens of degrees Kelvin. The cosmic background radiation permeating interstellar space is a remnant from the Big Bang, creating a dim glow that infuses the universe. Cosmic rays, high-energy particles originating from various cosmic events, permeate interstellar space and can pose significant risks to spacecraft and astronauts. These rays travel almost at the speed of light and consist mainly of protons and atomic nuclei. Interstellar space also experiences magnetic fields and dynamic influences from nearby stars, supernova remnants, and galactic structures, which can impact the movement of particles and shape local interstellar conditions. Overall, interstellar space is an environment marked by vast emptiness, low temperatures, and the presence of rarefied materials, creating a unique backdrop for understanding the processes that govern star formation and the expansive nature of our universe. Exploring these conditions reveals fundamental insights into the very fabric of the cosmos and the dynamics that operate on an interstellar scale. Organisms on Earth that thrive in extreme environments provide valuable insights into the potential for life on other worlds. These extremophiles can survive conditions that seem inhospitable to most life forms, such as extreme temperatures, high radiation levels, acidic or alkaline environments, and high-pressure surroundings. Studying these resilient organisms helps scientists expand their understanding of what constitutes a viable habitat, which is crucial for astrobiology, the study of potential life beyond Earth. One striking example is thermophiles, which are bacteria that thrive in high-temperature environments such as hot springs and hydrothermal vents. These organisms have adapted their cellular structures and enzymes to function optimally at temperatures that would denature proteins in most other living beings. The study of thermophiles informs the search for life on planets or moons, like Jupiter's Europa or Saturn's Enceladus, where subsurface oceans may exist under ice, possibly harboring similar extremophilic life forms. Halophiles are another type of extremophile that adapted to extremely salty environments, such as salt flats or salt mines. These organisms can provide insights into how life might exist in regions with high salinity, which could be relevant in understanding environments like Mars or the subsurface oceans of icy moons, where salinity levels may vary dramatically. The biochemical adaptations of halophiles can help astrobiologists gauge what sorts of metabolic processes might be plausible in extraterrestrial environments with high salt concentrations. Moreover, organisms that can withstand intense radiation, like certain types of bacteria found in the Chernobyl exclusion zone, shed light on how life might survive on planets or moons with high radiation levels, such as those exposed to cosmic rays or solar flares in space. Understanding the genetic and biochemical resilience of these organisms helps scientists assess the potential for survival in climates considerably harsher than what is found on Earth. By exploring the adaptations of extremophiles, researchers can refine their theories on habitability and the types of life forms that might exist under various environmental conditions across the solar system and beyond. This knowledge aids in defining the parameters for astrobiological missions and fosters optimism about the possibility of finding life in some of the most unlikely places in the universe. Radiation levels in our solar system vary significantly depending on the region and the protective influence of planetary atmospheres and magnetic fields. Near the Sun, radiation levels are considerably higher due to solar radiation, which includes a wide spectrum of electromagnetic waves, from radio waves to gamma rays, as well as energetic particles such as protons and electrons. The solar wind, a continuous stream of charged particles emitted by the Sun, contributes to this high radiation environment, especially in regions close to the star. In the inner solar system, particularly on planets like Mercury and Venus, the radiation levels are extreme. Mercury, lacking a significant atmosphere, is directly exposed to solar radiation, leading to intense heat during the day and colder temperatures at night. Venus, though shrouded in thick clouds, still receives high levels of solar radiation, complicating any potential for human exploration. As we move outward to the Earth, our planet's atmosphere and magnetic field provide essential protection against harmful radiation. The magnetic field deflects solar winds and cosmic rays, and the atmosphere absorbs a significant portion of ultraviolet radiation. However, beyond the protective shield of Earth's atmosphere, radiation levels increase, particularly in the higher layers of the atmosphere and in space. In the regions of outer space and around gas giants like Jupiter and Saturn, radiation levels can become particularly hazardous. Jupiter, for example, has an incredibly strong magnetic field that captures high-energy particles, creating extensive radiation belts known as the Van Allen belts. These belts contain intense levels of radiation that pose severe risks to spacecraft and would be lethal to humans without significant shielding. Farther out in the solar system, such as in the Kuiper Belt and beyond, radiation levels decrease markedly. In these distant regions, the density of solar wind and cosmic radiation is much lower, creating a more benign radiation environment compared to the inner planets. Overall, understanding the radiation levels throughout the solar system is crucial for planning future space missions, designing spacecraft, and ensuring the safety of astronauts venturing to other worlds. These variations in radiation highlight the protective roles of planetary atmospheres and magnetic fields and inform our knowledge of habitability in different cosmic environments. Gas giants like Jupiter generate their powerful magnetic fields primarily through a process known as the dynamo effect. This phenomenon occurs within the planet's interior, where a combination of conductive materials, rapid rotation, and turbulent motions creates a complex system that generates magnetic fields. Jupiter is particularly notable for its immense magnetic field, which is about 20 times stronger than Earth's. At the heart of Jupiter's magnetic field generation lies its metallic hydrogen core. Under the extreme pressure and temperature conditions present deep within the planet, hydrogen exists in a metallic state. This metallic hydrogen is a highly conductive fluid that plays a crucial role in the dynamo process. As the planet rapidly rotates, completing one rotation approximately every 10 hours, this conductive fluid moves and flows in turbulent patterns driven by convection currents caused by heat emanating from Jupiter's core. The movement of electrically charged particles within this metallic hydrogen generates electric currents, which in turn create magnetic fields. These magnetic fields are shaped by the dynamics of the fluid motion and are amplified as they intertwine with the planet's motion. As a result, Jupiter's magnetic field extends far beyond its surface and is intricately related to the planet's rotation and the properties of the materials in its interior. Additionally, Jupiter's strong magnetic field encompasses a vast magnetosphere, which is a region dominated by the planet's magnetic influence, extending millions of kilometers into space. This magnetosphere captures charged particles from the solar wind and is the cause of many phenomena, including auroras near Jupiter's poles. These interactions can produce radiation belts similar to Earth's Van Allen belts, but with intensity far surpassing those found on our own planet. The study of Jupiter's magnetic field not only provides insights into the internal structure and dynamics of this gas giant, but also enhances our understanding of similar magnetic processes that may occur on other gas giants, both within and beyond our solar system. Gravity has a profound effect on the passage of time, a concept that arises from Albert Einstein's theory of general relativity. According to this theory, the presence of mass causes a curvature in spacetime, the four-dimensional fabric that merges the three spatial dimensions with time. The stronger the gravitational field, the more pronounced the curvature, which influences how time is experienced. In practical terms, this means that time runs slower in stronger gravitational fields compared to areas where gravity is weaker. For example, clocks located at sea level, where the gravitational pull of Earth is strongest, run slightly slower than those located at higher altitudes where gravity is weaker. This effect has been measured using extremely precise atomic clocks placed at different elevations. The difference, though minuscule, aligns perfectly with predictions made by general relativity. An even more dramatic illustration of gravity's effect on time occurs near extremely massive objects, such as black holes. Close to a black hole's event horizon, the gravitational pull becomes so intense that time dilation becomes significantly pronounced. For an observer far from the black hole, time appears to move much more slowly for anything falling into or orbiting near the black hole. This means that if a spaceship were to orbit a black hole, the crew aboard would experience time at a different rate compared to someone watching from a safe distance. This phenomenon has practical implications, particularly for technologies such as the Global Positioning System or GPS. Satellites orbiting Earth experience both gravitational time dilation, due to their altitude being farther from Earth's mass, and special relativity effects from their speeds. As a result, two types of corrections must be applied to ensure that the satellite clocks synchronize correctly with clocks on the ground, demonstrating that the effects of gravity on time are not just theoretical, but also fundamental to the functioning of modern technology. Overall, the interplay between gravity and time fundamentally reshapes our understanding of the universe, illustrating how the very fabric of reality is influenced by the presence of mass. The concept of spacetime combines the three dimensions of space, length, width, and height, with time into a single four-dimensional continuum. This revolutionary idea arose from Albert Einstein's theories of special and general relativity. In classical physics, space and time were viewed as separate entities. However, Einstein's framework illustrates that they are interwoven, fundamentally affecting how we perceive the universe. In this four-dimensional model, events are positioned not just by their spatial coordinates, but also by their time of occurrence. For example, specifying an event in spacetime requires both where and when it happens. This interconnection leads to intriguing consequences, such as time dilation, where time can pass at different rates depending on the relative motion of observers or the strength of gravitational fields, a consequence evident in the behavior of satellites in orbit. Spacetime also changes the way we understand gravity. Rather than merely being a force acting at a distance, gravity is conceptualized through the curvature of spacetime caused by mass. Massive objects like planets and stars warp the fabric of spacetime around them, creating dents that other objects move along, akin to how a marble rolls along a curved surface. This curvature explains why planets orbit stars and why objects fall towards Earth. Thus, gravitational interactions occur not through direct force, but through the geometric properties of spacetime. Moreover, the idea of spacetime invites profound considerations regarding the nature of the universe, including concepts such as black holes and the expansion of the universe itself. For instance, inside a black hole, spacetime is so warped that not even light can escape, leading to regions where the known laws of physics cease to apply. Overall, the concept of spacetime not only reshapes our understanding of gravity and motion, but also fundamentally impacts cosmology, defining how we understand the universe's structure, origin, and evolution. This framework continues to guide scientific inquiry and shape our exploration of the cosmos, revealing the intricate relationships between time, space, and the matter that populates the universe. Astronomers have a unique ability to look back in time when observing distant celestial objects, and this is fundamentally tied to the speed of light. Light from stars and galaxies takes time to travel to Earth. So when we observe these objects, we are actually seeing them as they were in the past, not as they exist in the present moment. This phenomenon occurs because light travels at a finite speed, approximately 300,000 kilometers per second in a vacuum. For example, if a star is located 10 light-years away, the light we observe from it today left the star 10 years ago. Therefore, we see the star as it was a decade in the past. This time lag becomes even more pronounced with more distant objects. When astronomers look at galaxies billions of light-years away, they are witnessing phenomena that occurred billions of years ago, allowing them to study the early stages of the universe's evolution. Telescopes play a crucial role in this process. Powerful instruments like the Hubble Space Telescope and the upcoming James Webb Space Telescope are able to detect light across various wavelengths, including visible light, ultraviolet, and infrared. By observing light emitted from distant objects across these wavelengths, astronomers can gather information about the universe at different points in time. For instance, observing the light from ancient galaxies gives insight into when they formed, their structure, and how they have evolved. This ability to look back in time also enables scientists to study cosmic events such as the formation of stars, supernova explosions, or even the moments immediately after the Big Bang through the cosmic microwave background radiation. By piecing together data from various parts of the universe, astronomers can construct a detailed timeline of cosmic history, effectively mapping out the evolution and development of the universe from its infancy to the present day. The implications of looking back in time extend beyond mere observation. This practice allows scientists to test and refine their theories about the universe's structure, composition, and the fundamental processes that govern it. Thus, observing distant objects serves as a vital tool in unraveling the mysteries of the universe, making the study of the cosmos a fascinating journey through time itself. The cosmic calendar is a fascinating conceptual tool that compresses the vast history of the universe into a single year, providing a perspective that helps us understand the relative timing of cosmic events. In this model, the entire 14 billion-year history of the universe is scaled down to just one calendar year, allowing us to visualize critical events in a more comprehensible and relatable manner. In the cosmic calendar, the Big Bang occurs at midnight on January 1st. The formation of the first stars and galaxies takes place around late February, while the Milky Way galaxy forms in early May. The solar system, including Earth, forms approximately 4.5 billion years ago, which corresponds to early September on the calendar. The emergence of life on Earth happens in late September, with simple single-celled organisms appearing first. Complex multicellular life begins to develop in late November, and the age of dinosaurs accounts for much of December, as they roam the Earth from about 250 million years ago until around 65 million years ago. Modern humans, Homo sapiens, appear in the last days of December, specifically on December 31st. However, anatomically, modern humans have only existed for about 200,000 years, which is represented as a mere few seconds on the cosmic calendar. Notably, recorded human history is even more recent, amounting to just the last few minutes of December 31st. This perspective highlights not only the vastness of cosmic time, but also the relatively brief duration of human existence in comparison to the age of the universe. It emphasizes the rapid pace of change and the long stretches of time preceding human civilization, providing context for our place in the cosmos. By putting cosmic events into a more relatable format, the cosmic calendar deepens our appreciation for the immense scales involved and encourages reflection on the interconnectedness of life and the universe. Ultimately, it serves as a reminder of both our brief existence and the immense history that led to the development of life on Earth. Time dilation, a profound effect predicted by Einstein's theories of relativity, could significantly impact future space travelers, particularly those embarking on long journeys at high speeds or in strong gravitational fields. Time dilation occurs because time is perceived to pass at different rates depending on relative speed and gravitational influence. For example, if astronauts were to travel close to the speed of light, they would experience time more slowly compared to people remaining on Earth. This means that while they might only age a few years during their journey, many more years could pass on Earth. This effect is not merely theoretical. It has been confirmed through experiments, such as those involving atomic clocks on fast-moving aircraft or satellites. Future space missions that venture into deep space or approach the speed of light could have astronauts returning to find that their friends and family have aged significantly while they have scarcely aged at all. Additionally, time dilation can occur due to the influence of gravity. For instance, if space travelers were to live or work on a planet with much stronger gravity than Earth, such as near a massive celestial body like a black hole, they would experience time at a slower rate compared to those on Earth. This means that astronauts in a strong gravitational field could find themselves aging more slowly relative to the wider universe. Such effects raise intriguing possibilities and challenges in both planning space missions and understanding human experiences in space. For example, if a mission occurred in a strong gravitational field or involved significant velocities, astronauts would need to consider how time dilation could impact their communication with Earth and their return journey. Decisions about how to manage their time and potential emotional consequences of being away for longer periods would become critical. Time dilation could affect future space travelers in profound ways, altering their experiences of time and relationships with those on Earth. As human exploration ventures farther into the cosmos and approaches the extremes of relativity, understanding these effects will be essential for mission planning and the psychology of space travel. The concept of proper time in relativity refers to the time measured by a clock that is at rest relative to the observer and moving along with the observer. It represents the actual time interval experienced by an object or observer as they travel through spacetime. Since the speed of light is constant in all reference frames, the amount of proper time is affected by the relative motion and gravitational field experienced by an object. In the context of special relativity, proper time is particularly significant when considering scenarios involving high speeds. When an object moves close to the speed of light, the time experienced by that object as measured by a clock traveling with it will be less than the time measured by a stationary observer due to time dilation. This means that while the moving object may perceive a shorter duration passing, an outside observer will measure a longer time interval for the same event. The proper time is the minimum time interval that can be measured between two events in spacetime, as it is independent of any outside influences or frames of reference. In the realm of general relativity, the concept of proper time also incorporates the influence of gravity. As gravitational fields become stronger, the proper time experienced by someone in that field will differ from that experienced by someone farther away. For example, a clock on the surface of a massive planet will run slower relative to a clock in deep space. Thus, the proper time experienced by an observer in a strong gravitational field compares to a reference observer in a weaker field or in free space. Proper time provides a vital foundation for understanding how time is perceived differently depending on the movement and gravitational context of observers. It plays a crucial role in developing the equations that govern time dilation and contributes to our comprehension of time as a dimension that is fundamentally intertwined with space. Through this lens, relativity reshapes our conceptions of time, showcasing its variability and the effects of relative motion and gravity on the way we experience the universe. Atomic clocks operate based on the principles of quantum mechanics and the behavior of atoms, specifically the vibrations or transitions between energy levels in atoms. Unlike traditional clocks that rely on mechanical parts or the oscillation of a pendulum, atomic clocks use the natural frequency of microwave radiation emitted or absorbed by atoms to keep time with incredible precision. The most common type of atomic clock uses cesium atoms. In these clocks, a beam of cesium atoms is passed through a microwave field. When the microwave frequency matches the natural frequency of the cesium atoms, the atoms transition between two energy states. The clock is designed to count these transitions, allowing it to measure time based on these consistent and predictable atomic oscillations. The standard definition of the second is based on the vibrations of cesium atoms, specifically the duration of 9,125,000,000 vibrations, which reinforces the precision of atomic clocks. Atomic clocks are critically important for space exploration for several reasons. First and foremost, they provide highly accurate timekeeping essential for navigation and positioning. Global positioning systems rely on a network of satellites equipped with atomic clocks to provide precise location data. When a satellite transmits its position, the device on Earth calculates the time it took for the signal to arrive, requiring precise synchronization of time between the satellite and the receiving device. This time, synchronization allows for accurate distance measurements and positioning. So, in addition to navigation, atomic clocks are crucial for experiments in physics and fundamental research in space. For instance, researchers study time dilation effects based on relative motion and gravitational fields, making atomic clocks fundamental instruments for testing theories of relativity. When astronauts travel in space, the effects of both speed and gravity can cause time differences between their clocks and those on Earth. Accurate atomic clocks can measure these differences, providing insights into relativistic effects in practical applications. Furthermore, precise timekeeping is necessary for coordinating remote space missions and ensuring that various spacecraft remain in sync for various operations, such as docking maneuvers or cell communication. As space exploration continues to advance, the role of atomic clocks will remain pivotal for ensuring safe and effective exploration of our solar system and beyond. Near the event horizon of a black hole, time experiences extreme dilation effects, influenced by the intense gravitational field produced by the black hole's mass. According to Einstein's theory of general relativity, the closer an object gets to a massive body, the more significant the curvature of spacetime becomes, affecting the flow of time. At the event horizon, which is the boundary beyond which nothing can escape the black hole's gravitational pull, this effect becomes particularly pronounced. For an observer located far away from the black hole, time for an object approaching the event horizon appears to slow down dramatically. As the object gets closer, it will seem to the distant observer that the object is moving slower and slower and eventually becomes frozen at the event horizon. Any light signals emitted from the object also struggle to escape the gravitational grip of the black hole, making it increasingly difficult for the observer to see the object as it nears the event horizon. Ultimately, the light will be redshifted, meaning it loses energy and shifts to longer wavelengths, fading and becoming undetectable. On the other hand, from the perspective of the object falling into the black hole, time continues to pass normally. The object itself does not experience any unusual effects on its internal clock as it crosses the event horizon. It would proceed through the event horizon as if nothing special were happening, although the extreme conditions beyond that boundary would likely lead to a rapid compression and eventual destruction due to tidal forces, a process often referred to as spaghettification. This difference in time perception underscores a fundamental aspect of relativity. Time is not an absolute measure. Instead, it is influenced by the curvature of space-time created by mass. The peculiar nature of time near a black hole not only challenges our understanding of physics, but also poses profound questions about the nature of reality and the fate of information once it crosses the event horizon. As scientists continue to explore these mysteries, the study of black holes reveals the fascinating and extreme behaviors of time and space. The expansion of the universe has a profound influence on our perception of time, particularly when considering cosmic scales. This dynamic expansion means that galaxies are moving away from us, and the further away they are, the faster they appear to be receding. As a result, the concepts of time and distance become intertwined in unique ways, reshaping how we understand the timeline of the universe. One significant aspect is the relationship between distance and the time it takes for light from distant galaxies to reach us. When we observe light from a galaxy billions of light-years away, we are not seeing it as it is today. Instead, we are looking back into the past because it has taken billions of years for that light to travel across the expanding universe to our eyes. Consequently, astronomers use this information to piece together a history of the universe, effectively reconstructing the sequence of events that have led to the present state of cosmic structures. Additionally, the expansion of the universe contributes to the phenomenon known as redshift, which is the stretching of light waves as they travel through expanding space. This redshift affects our observation of light from distant galaxies, altering the wavelengths of the light we see. The greater the distance, the more significant the redshift, leading to shifts that can provide clues about the rate of expansion and the universe's age. The nuances of redshift create a complex interplay between distance, time, and the rate of expansion, complicating our understanding of how time is experienced at cosmic distances. Moreover, the expanding universe influences the ultimate fate of cosmic structures. As the expansion continues, many galaxies will eventually move beyond our observable horizon. This means that over vast timescales they will recede so far that their light will no longer reach us, resulting in a diminishing view of the cosmos. Consequently, distant civilizations or future observers could find themselves in a universe that appears increasingly void of galaxies, fundamentally altering their perception of cosmic time. The expansion of the universe reshapes our perception of time on a cosmic scale by interlinking distance and time, affecting the light we observe from distant celestial bodies and influencing the long-term behavior of the universe. This complex relation highlights the intricacy of cosmic time and underlines the dynamic nature of the universe itself, providing a deeper understanding of its past, present, and future. The concept of the arrow of time refers to the directional flow of time from the past to the future, which corresponds to our observation that certain processes are irreversible. This idea encapsulates why events occur in a particular order and helps distinguish the past from the future. The arrow of time can be understood in various contexts, such as thermodynamic, psychological, and cosmological arrows. The thermodynamic arrow of time is perhaps the most well-known, rooted in the second law of thermodynamics, which states that the entropy of an isolated system tends to increase over time. Entropy is a measure of disorder or randomness, and as systems evolve, they naturally transition from states of lower entropy to higher entropy. This means that complex structures tend to break down into simpler, more disordered states over time. For example, a hot cup of coffee in a cold room will eventually cool down, moving toward a state of thermal equilibrium, thereby illustrating the progression from order to disorder. In the context of the universe's evolution, the arrow of time is closely linked to its expansion. The Big Bang marks the beginning of our universe, a singular moment of high energy and low entropy. As the universe expanded and cooled, structures began to form, stars, galaxies, and eventually life, creating pockets of order amidst the increasing total entropy of the universe. This expansion reflects a directionality of time where the past is characterized by lower entropy and the future by increasing entropy. Additionally, the psychological arrow of time reflects our human perception of time, where we remember past events but not future ones. This perception aligns with our experiences and interactions with the world, where we perceive change and growth, reinforcing our understanding of time's flow from past to future. In cosmological forums, the arrow of time has fundamental implications for how we understand the universe's fate. As time progresses and entropy continues to rise, the universe may head toward a state of maximum entropy, often referred to as the heat death of the universe. In this scenario, all thermodynamic processes fail to operate, leading to a uniform distribution of energy and the cessation of all physical processes as we know them. The arrow of time encapsulates the unfolding of events from the past to the future across various domains, illuminating our understanding of irreversible processes, entropy, and the evolution of the universe. It serves as a crucial concept in both physics and philosophy, guiding our inquiries into the nature of reality and the temporal aspects of existence. Terraforming Mars to make it habitable for humans is a complex and multifaceted challenge that entails altering the planet's environment and climate to support life. While significant scientific advancements would be required, various theoretical methods have been proposed to initiate this process, targeting factors such as temperature, atmosphere, and water availability. One of the primary goals of terraforming Mars is to thicken its atmosphere to provide adequate pressure and composition for human life. Current Martian atmosphere is very thin and composed mostly of carbon dioxide, making it inhospitable. One proposed approach involves releasing greenhouse gases to warm the planet, increasing surface temperatures and pressure. This could be achieved by utilizing technologies to produce gases such as carbon dioxide, methane, or ammonia, potentially sourced from Martian resources or brought from elsewhere in the solar system. Additionally, giant mirrors or orbital solar reflectors could be deployed to redirect sunlight towards the Martian surface, further heating the planet and facilitating atmospheric changes. In parallel to thickening the atmosphere, water availability plays a critical role in making Mars habitable. One possibility is melting the polar ice caps, which are composed of frozen carbon dioxide and water ice, to release these resources into the environment. That process could not only increase liquid water, but also contribute to elevating atmospheric pressure and temperature. While the presence of water on Mars could sustain life, it may also need to be artificially introduced through the importation of ice asteroids or comets to provide additional water resources. Another essential aspect is developing a sustainable biosphere that can support human life. Introducing specially designed microorganisms and plants that can thrive in Martian conditions might be an effective approach. These organisms could help convert carbon dioxide into oxygen and organic matter, gradually building a self-sustaining ecosystem. Ensuring the growth of these organisms would also involve creating suitable soil and leveraging Martian regolith as a medium for planting. Moreover, any terraforming endeavor would need to consider the long-term implications of such changes, including ethical considerations regarding the preservation of potential Martian life forms or ecosystems. The time frame for achieving a habitable environment on Mars is projected to span centuries, if not longer, requiring sustained efforts and advancement in technology. Overall, while terraforming Mars presents myriad challenges, the scientific exploration of this idea encourages innovative thinking about planetary science, sustainability, and the broader implications of humanity's place in the universe. As our knowledge and technology progress, the possibility of transforming Mars into a habitable environment for humans remains an exciting frontier for future exploration. The possibilities for interstellar travel, or reaching other star systems beyond our solar system, have long fascinated scientists, engineers, and dreamers alike. While current technology limits human space exploration to within our solar system, several theoretical concepts and emerging technologies hold promise for making interstellar travel a reality in the distant future. One of the most discussed concepts is the use of spacecraft propelled by fusion energy, akin to the drive systems seen in science fiction. Fusion propulsion would harness the energy released during nuclear fusion reactions, potentially providing an immense thrust necessary for long journeys to nearby star systems, such as Proxima Centauri or Alpha Centauri. Several proposals have considered using fusion-powered spacecraft, which could theoretically sustain constant acceleration for an extended period, significantly reducing travel times compared to traditional chemical rockets. Another intriguing possibility is the concept of a solar sail or laser sail. These spacecraft would utilize giant reflective sails pushed by the pressure of sunlight or powerful lasers from Earth or space-based installations. With sufficient energy, a laser sail could reach a fraction of the speed of light, enabling travel across light years in a relatively short time frame. Projects like the Breakthrough Starshot initiative are exploring this idea, aiming to develop a tiny, lightweight spacecraft that could theoretically reach nearby stars within a generation if successful. Theoretical concepts such as wormholes or warp drives offer even more speculative possibilities. Wormholes, as envisioned in theoretical physics, could create shortcuts through spacetime, potentially allowing for instantaneous travel between distant points. Similarly, a warp drive would manipulate the fabric of spacetime, contracting it in front of the spacecraft and expanding it behind to achieve faster-than-light travel. However, these concepts remain purely theoretical, with no experimental evidence or practical methods for their construction currently available. Furthermore, interstellar travel poses numerous challenges apart from the propulsion systems. Spacecraft would need to be equipped to sustain human life for extended periods, addressing issues like radiation exposure, life support systems, and psychosocial factors. There is also the question of propulsion systems developing the necessary speeds to ensure travel within human timescales, as journeys could take decades or even centuries with current technology. The prospect of interstellar travel encourages not only advancements in science and engineering, but also philosophical inquiries about humanity's place in the universe. As research continues in astrophysics, propulsion technologies and related fields, the dream of reaching other star systems will remain a tantalizing possibility, driving exploration and inspiring future generations to push the boundaries of what is achievable. Advanced civilizations might harness the energy of entire stars or galaxies through several theoretical concepts that extend beyond our current capabilities. These ideas often stem from the hypothetical use of massive engineering projects and technologies that capture and utilize energy on a grand scale, reflecting the notion of a Kardashev-scale civilization. This scale categorizes civilizations based on their ability to harness energy. A Type 1 civilization utilizes all available energy resources on its home planet. A Type 2 civilization captures energy at the scale of its star. And a Type 3 civilization governs energy on the scale of an entire galaxy. A prominent method for a Type 2 civilization to harness energy from a star is through the construction of a Dyson sphere. Proposed by physicist Freeman Dyson, a Dyson sphere is a hypothetical megastructure that would encompass a star, capturing a significant portion of its emitted energy. There are various designs for Dyson spheres, ranging from solid shells to swarms of solar collectors or satellites that orbit the star. This technology could theoretically allow an advanced civilization to gather energy sufficient to power immense projects or even support advanced technologies and interstellar travel. Another potential method is the use of stellar energy harnessing techniques, such as stellar mining. This concept involves extracting useful materials from stars, such as hydrogen for fusion power generation, and could provide an almost limitless energy source for civilizations capable of reaching a star's core. Reaching a star's surface, however, would present numerous challenges due to extreme temperatures and radiation, making this a very low probability method at our current technological level. For Type 3 civilizations, harnessing the energy of an entire galaxy could take the form of manipulating cosmic structures such as black holes or supermassive stars. One hypothetical idea involves building a structure around a black hole called a Dyson net, or utilizing its immense gravitational energy to extract usable power through processes like gravitational slingshots. This could involve directing star matter and energy flow to feed a civilization's energy needs. Additionally, advanced civilizations could exploit the cosmic microwave background radiation, the faint afterglow of the Big Bang, as a source of energy. While this radiation is extremely diffuse, it represents a significant energy reservoir on a cosmic scale. Innovative technologies could be developed to capture this energy and convert it into usable forms. While these ideas remain largely theoretical and far beyond current human capabilities, they push the boundaries of our understanding of physics and engineering. The exploration of how advanced civilizations might harness stellar and galactic energy invites deeper contemplation about the future of humanity and the potential for life beyond our own planet. As our technologies advance, concepts like those associated with the Kardashev scale stimulate our imagination regarding the vast possibilities that the universe offers. Detecting advanced alien civilizations remains one of the most profound challenges in astrobiology and astrophysics. Several proposed methods aim to uncover signs of extraterrestrial intelligence, often focusing on the impact these civilizations might have on their surroundings. Here are some of the most notable methods. One widely discussed approach is the search for technosignatures, which are indicators of technology or industrial activity similar to our own. This could include the detection of radio signals, which have been a focus of initiatives like the Search for Extraterrestrial Intelligence, or SETI. Advanced civilizations might transmit purposeful communications or generate leakage signals inadvertently from their technologies, such as radar, television broadcasts, or other electronic devices. By scanning specific regions of the sky using radio telescopes, scientists aim to intercept such emissions, hoping to find patterns or signals that indicate intelligent origins. Another promising method involves looking for megastructures around distant stars, such as the aforementioned Dyson sphere. A Dyson sphere would produce significant thermal emissions, detectable through infrared telescopes. If a star exhibits unusual patterns in its brightness or spectral profile, It could indicate the presence of a structure designed to capture energy on a grand scale. Observations made by space telescopes could help identify such anomalies, potentially pointing to advanced engineering efforts by extraterrestrial civilizations. The study of exoplanets is also essential in the quest for alien life. By examining atmospheres of planets in habitable zones around stars, scientists can search for biosignatures and technosignatures. Such signatures might include gases like oxygen or methane in unusual concentrations, which could suggest the presence of biological activity or industrial processes. Missions like the James Webb Space Telescope will contribute significantly to this endeavor by providing high-resolution spectroscopic data on distant planets. Additionally, scientists propose that investigating cosmic-scale phenomena like unusual astronomical events could provide clues to the existence of advanced civilizations. For example, observing periodic or anomalous variations in brightness from stars or strange gravitational patterns may indicate artificial manipulation of celestial bodies. Some hypotheses even consider more exotic scenarios, such as examining neutron star collisions for signs of artificial signals or transmissions. Finally, the search for artificial light emissions in space poses another intriguing avenue. Light pollution from advanced civilizations could extend far beyond their planets, potentially observable over interstellar distances. If significant light sources, such as cities or power plants, could be detected, it might suggest the presence of intelligent life. The detection of advanced alien civilizations remains speculative, and while our attempts to uncover extraterrestrial intelligence are ongoing, each method contributes uniquely to our understanding of the cosmos. With advancements in technology and innovative approaches, the future may yield promising breakthroughs in our quest to answer one of humanity's most profound questions. Are we alone in the universe? Colonizing the moons of gas giants in our solar system presents an exciting possibility for future human settlement and exploration. Moons like Europa, Ganymede, and Titan are of particular interest due to their potential for resources and habitability in some form. While the challenges are significant, theoretical strategies exist for establishing human presence on these distant worlds. One primary consideration is determining the feasibility of locating resources for sustenance and construction. For instance, Europa, one of Jupiter's moons, is believed to have a subsurface ocean beneath its icy crust. If accessible, this water could support human life and provide hydrogen and oxygen for fuel and life support systems. Establishing methods for melting or drilling through the ice to access this ocean would be a critical first step. Similar strategies could be applied to Titan, Saturn's largest moon, which harbors lakes and rivers of liquid methane and ethane, potentially usable for energy. Once resources are identified, the next phase involves developing habitats that can withstand the harsh environmental conditions of these moons. Gas giants' moons often experience extreme cold and radiation exposure. For example, Europa's surface temperatures can drop below -100 degrees Celsius, requiring robust and insulated structures to ensure human safety. This habitat construction might use local materials in addition to prefabricated components sent from Earth, creating inflatable habitats, or utilizing 3D printing technologies to build structures from the moon's regolith. Transporting humans and supplies to these distant locations would also need careful planning. Given the distances involved, efficient propulsion systems and possibly in-orbit refueling strategies would be required for crewed missions. Once in space, establishing a transport network that can ferry materials, equipment, and personnel between Earth and the moons will be crucial for sustaining long-term colonies. Life support systems would need to be carefully engineered to recycle air, water, and waste to create a self-sufficient environment. Growing food in controlled environments with artificial lighting or hydroponics could help ensure a steady food supply without relying solely on resupply missions from Earth. Social and ethical considerations accompany the colonization of other worlds as well. Questions about planetary protection protocols and the potential for existing microbial life on moons like Europa complicate the discussion on human settlement. Developing guidelines and frameworks for responsible exploration and colonization will be essential to navigate these ethical dilemmas. While colonizing the moons of gas giants presents significant technical, logistical, and ethical challenges, the potential for harnessing their resources and expanding human civilization beyond Earth is a compelling prospect. As technology advances and our understanding of these celestial bodies deepens, the dream of establishing a human presence on the moons of gas giants may one day transform into reality. Several ambitious plans for next-generation space telescopes are being developed to succeed and complement the capabilities of the James Webb Space Telescope. These future telescopes aim to enhance our understanding of the universe, exploring everything from distant galaxies and exoplanets to the fundamental nature of dark matter and dark energy. One prominent project is the Roman Space Telescope, previously known as W-FIRST, scheduled for launch in the mid-2020s. This telescope will have a wide field of view, approximately 100 times larger than that of the Hubble Space Telescope, allowing astronomers to survey vast areas of the sky efficiently. Its primary goals include investigating the nature and distribution of dark energy through observations of supernova and gravitational lensing, as well as searching for exoplanets using techniques like microlensing. Another exciting mission is the European Space Agency's Euclid, which also aims to explore dark energy and dark matter. Scheduled for launch in the early 2020s, Euclid will use a wide-field visible and near-infrared instrument to create a three-dimensional map of the universe, detailing how galaxies are distributed across space and time. Insights gained from this mission will help address fundamental questions about the universe's expansion and the underlying forces shaping it. Looking further ahead, the Habitable Exoplanet Observatory, or HABEX, and the Large Ultraviolet Optical Infrared Surveyor are two proposed concepts under consideration by NASA. HABEX aims to detect and analyze the atmospheres of potentially habitable exoplanets around nearby stars, with advanced coronagraph technology designed to block out the light from stars to observe the faint light reflected from planets. LUVOIR, on the other hand, would be a large observatory capable of observing a wide array of cosmic phenomena, including exoplanet imaging, galaxy formation, and the evolution of the universe. Additionally, concepts like the Origins Space Telescope look to go beyond current observational capabilities, focusing on the formation of stars and galaxies, as well as the origins of life within the universe. By observing in far infrared wavelengths, this telescope would provide insights into cool and distant astronomical objects. Each of these proposed missions builds on the capabilities of existing telescopes while introducing advanced technologies to tackle some of the most pressing questions in astrophysics. These next-generation space telescopes will enhance our understanding of the universe's history, the formation of celestial bodies, and the potential for life beyond Earth, inspiring future generations of astronomers and explorers in their quest to unravel cosmic mysteries. Deflecting a potentially hazardous asteroid headed for Earth is a topic of great concern for planetary defense, and several strategies have been proposed to address this imminent threat. These methods aim to alter the asteroid's trajectory enough to prevent a collision, thus preserving life on our planet. Here are some of the most discussed techniques. One prominent approach is the kinetic impactor technique. This method involves sending a spacecraft to collide with the asteroid at high speeds, transferring momentum and changing its velocity. By impacting the asteroid ahead of time, ideally years before the potential collision, the spacecraft can create a small but significant alteration in the asteroid's path. NASA's Double Asteroid Redirection Test mission is designed specifically to test this technique by targeting Didymos, a binary asteroid system aiming to demonstrate the effectiveness of this method in altering the asteroid's trajectory in a controlled environment. Another potential method is the use of a gravity tractor. This approach relies on the subtle gravitational attraction between a spacecraft and the asteroid. By positioning a spacecraft near the asteroid for an extended period without landing on it, the spacecraft's gravitational pull can gradually alter the asteroid's orbit. While this method requires significant time, potentially years or decades, it allows for a more controlled and gentle deflection, which might be particularly useful for smaller asteroids. A third strategy involves the use of nuclear devices. If an asteroid is large and heavily resistant to non-destructive methods, detonating a nuclear device near the asteroid could help change its trajectory. This approach would not involve a direct impact, but rather a nuclear explosion at a safe distance, allowing for the blast wave or vaporization of the surface material to impart a force that nudges the asteroid off course. However, this method comes with considerable risks, including fragmentation that could create multiple hazardous pieces heading toward Earth. Additionally, some researchers have proposed using solar sails or reflectors to harness the energy from sunlight. By deploying reflective material that can create a small but continuous force from solar radiation, an asteroid's path could gradually be altered over time. This method would require significant lead time to be effective, making it suitable for distant threats rather than immediate ones. Lastly, early detection and close monitoring of near-Earth objects are paramount for planetary defense. By establishing an extensive global network of telescopes and observation programs, scientists can identify potential threats many years in advance, providing the necessary time to implement one of the proposed deflection strategies effectively. In conclusion, while there is no one-size-fits-all solution for deflecting a potentially hazardous asteroid, a range of promising strategies exist. A combination of advanced technologies and early detection efforts could enhance our ability to safeguard Earth against cosmic threats, ensuring that we are prepared to mitigate risks from our solar system's dynamic environment. Using antimatter as a fuel source for spacecraft presents an intriguing possibility for achieving high-efficiency propulsion in space travel. Antimatter consists of particles that are the counterparts to ordinary matter, possessing the same mass but opposite charge. When matter and antimatter come into contact, they annihilate each other, releasing an immense amount of energy according to Einstein's equation E equals mc squared. This annihilation process could provide a remarkably potent energy source for propulsion systems. The theoretical energy output from the annihilation of antimatter is staggering. For instance, 1 gram of antimatter, when combined with 1 gram of matter, could yield around 100 billion joules of energy, equivalent to the energy produced by a small nuclear bomb. This high energy density means that in theory, a spacecraft could utilize small amounts of antimatter to achieve propulsion systems far more efficient than those based on chemical rockets or even nuclear fission. One potential application of antimatter in spacecraft propulsion is through antimatter-catalyzed propulsion. In this concept, antimatter would be used to initiate reactions in conventional propellant materials. The presence of antimatter would catalyze these reactions, leading to significantly enhanced thrust and efficiency. This method could produce the energy needed for deep space missions while using relatively small amounts of antimatter. Another promising approach involves the use of antimatter for direct propulsion. Antimatter rockets could, in theory, convert the energy released from annihilation into thrust in a propulsion system. This could be done either by using the resulting gamma radiation or by creating high-energy plasma from the annihilation products that could be expelled to generate thrust. However, the technical challenges in effectively harnessing and managing antimatter remain significant. Despite its potential, there are considerable hurdles to overcome before antimatter can be a practical fuel source for spacecraft. Producing antimatter is incredibly energy-intensive and currently requires significant resources. For example, producing just a few nanograms of antimatter can consume vast amounts of energy from conventional sources. Additionally, antimatter must be stored and handled in a way that prevents it from coming into contact with regular matter, which presents engineering challenges. Moreover, safety concerns arise as the storage and potential use of antimatter could lead to catastrophic results if not managed correctly. The annihilation events release not just energy, but also high levels of radiation, which would need stringent protective measures for any crewed missions involved. While the use of antimatter as a fuel source for spacecraft presents exciting possibilities with the potential for efficient deep space exploration, the technical, logistical, and safety challenges currently limit practical applications. As research continues and technology advances, antimatter propulsion may one day play a pivotal role in humanity's journey through the cosmos, opening new pathways for exploration and possibly even interstellar travel. Building and maintaining habitats in the harsh environment of space presents numerous challenges, including extreme temperatures, radiation exposure, microgravity, and the need for life support systems. However, various strategies and technologies are being developed to create sustainable living environments for future space exploration, whether on the Moon, Mars, or beyond. One of the key considerations in space habitat design is radiation protection. Space is filled with high-energy particles and cosmic rays that pose significant health risks to humans. To mitigate this, habitats could be constructed with thick shielding materials such as regolith or water, which are effective at absorbing radiation. On celestial bodies like the Moon or Mars, utilizing local materials to construct habitats offers an efficient way to provide this shielding while reducing the need to transport heavy materials from Earth. Another approach is to build habitats underground or within lava tubes, particularly on Mars or the Moon. These natural formations could provide substantial protection from radiation and micrometeorite impacts, while maintaining a stable temperature. Innovative construction methods, such as 3D printing using in situ resources, could be employed to create structures suited to these underground environments. Maintaining a habitable environment also requires effective life support systems that provide air, water, and food. Sustainability is vital, thus, closed-loop systems that recycle air and water will be essential. Advanced technologies like regenerative life support systems can treat and purify wastewater, convert carbon dioxide into oxygen, and manage waste. For example, biological systems using plants might produce oxygen and food while also filtering the air and recycling nutrients. Growing food in space presents another significant challenge, but it opens up exciting possibilities. Using hydroponics or aeroponics, astronauts can cultivate crops within controlled environments that utilize minimal water and space. Implementing vertical farming techniques within a habitat allows for maximizing food production while relying on energy-efficient LED lighting for plant growth. Moreover, maintaining the habitat's structural integrity and systems is crucial. Regular maintenance protocols, robust monitoring systems, and redundancy in critical systems will help ensure long-term habitation. Teleoperated or autonomous robots could assist astronauts in performing routine repairs and maintenance tasks, diminishing the risks associated with spacewalking or exposing humans to harsh conditions. Lastly, psychological and social well-being is essential for inhabitants living in confined spaces for extended periods. Designing habitats to allow for privacy, communal areas, and recreational facilities helps support mental health. Virtual reality or telecommunication systems could help inhabitants maintain connections with Earth, mitigating feelings of isolation and fostering a positive living environment. Overall, building and maintaining habitats in space requires innovative engineering, sustainable practices, and consideration of the psychological impacts on inhabitants. As advancements continue in technology and our understanding of environmental needs, the dream of sustainable living in the cosmos becomes increasingly achievable, paving the way for humanity's future beyond Earth. Creating artificial gravity on long-duration spaceflights is a crucial challenge for providing a more Earth-like environment for astronauts. Since prolonged exposure to microgravity can lead to various health issues, including muscle atrophy and bone density loss. Several proposed methods aim to simulate the effects of gravity in spacecraft. Here are some of the most discussed techniques. One of the primary methods for generating artificial gravity is rotational or centripetal acceleration through a spinning spacecraft. This approach utilizes the principle of centrifugal force, where a rotating structure creates a sensation of gravity for those inside. For instance, a spacecraft designed as a large rotating wheel or cylinder could cause occupants to experience artificial gravity along its outer surface. The radius of rotation and the speed of rotation would determine the level of artificial gravity experienced. This concept is often illustrated in science fiction, but it holds practical potential as research and engineering continue to refine designs for feasible implementation. Another proposed method is through linear acceleration, where a spacecraft continuously accelerates in a straight line to create a gravitational effect. By maintaining a constant acceleration over time, astronauts inside would experience a force similar to that of gravity. However, this approach requires a propulsion system capable of providing sustained thrust, which could be challenging over long distances, especially given the limitations of current propulsion technology. Additionally, concepts like the use of magnetic levitation or electrostatic forces have been explored as a way to simulate gravity. In this approach, specially designed systems would exert forces on astronauts or objects within the spacecraft, potentially providing a sensation similar to gravity. However, these methods remain largely theoretical and have not been extensively tested for practical applications in spacecraft. Implementing intermittent gravity or time-based cycles is another strategy under consideration. For instance, astronauts could spend portions of their time in artificial gravity environments with designated periods of microgravity for specific tasks. This method could help mitigate the effects of living in a zero-gravity environment while providing opportunities for exercise and muscle preservation during periods of artificial gravity. While these proposed methods showcase promising avenues for creating artificial gravity, extensive research and engineering efforts will be necessary to determine their feasibility, particularly concerning space travel's physical, psychological, and logistical aspects. Any practical solution will need to consider not only the technical challenges of implementation, but also the impact on the design, structure, and function of spacecraft for long-duration missions to destinations like Mars or beyond. Overall, the development of artificial gravity solutions will play a vital role in the health and well-being of astronauts during extended spaceflight, improving their performance and enhancing the sustainability of human exploration in the cosmos. As our journey through the cosmos comes to a close, we hope these fascinating space facts have expanded your understanding of the universe and perhaps even sparked new questions. From the tiniest particles to the largest structures in space, from the familiar planets of our solar system to the most distant galaxies, we've explored just a fraction of what the universe has to offer.